Hello there, and welcome to Science for Sleep, where curiosity settles in quietly and the universe slows to a thoughtful drift. You're in just the right place if you're winding down, looking for something soft but rich to rest your thoughts on. Tonight, we're asking a question that sounds simple at first, maybe even like the beginning of a child's wonder. But as it turns out, it's the kind of question that stretches in all directions the longer you look at it. Does the universe have a clock? Not a literal one, of course. Not a ticking piece of metal floating between stars, or a cosmic cuckoo popping out to mark the hours of galaxies. But is there something, anything, built into the fabric of space itself that keeps time? Something that says, in some fundamental way, this moment is now, and that one was before. It's the kind of question that feels like it should have an answer. After all, we use clocks constantly. They wake us up, they remind us when the soup is done, they quietly press on while we forget them. They are everywhere in our lives. Digital ones, analog ones, ones on walls, on wrists, on phones, on microwaves, even hidden inside our computers. But if you zoom out from Earth, past the weather and the traffic, past the atmosphere and the satellites, and keep going until you're floating among the stars, does the ticking continue, or does it stop? Is time something the universe itself keeps track of? Or is it just a system we invented, a way to give structure to change, a scaffolding for memory and planning? And maybe more personally, what time is it where you are right now? Is it late evening, when the streetlights glow and the dishes are done? Or is it early with the first hints of dawn slipping through the curtains? Maybe you're somewhere in between, in that quiet zone where the hours seem to blur a little. Whatever your moment looks like, thank you for choosing to spend it here. Wherever you're listening from, and whatever your little corner of the sky looks like right now, I hope this time feels like it belongs to you. If you find this kind of slow unraveling comforting, if the quiet pace of wandering through science helps ease your mind, it would mean a lot if you'd like the video or maybe subscribe. This sleepy little channel travels slowly, but every bit of encouragement helps it float a little farther into the algorithm's sky, and perhaps someone else who's wide awake and wondering at 1 a.m. might find it too. Now then, let's drift toward the question, gently, and see what's waiting in its centre. If you were to imagine the universe as a grand machine, an enormous system of stars and galaxies of energy and matter, you might expect there to be some sort of mechanism behind it all. A clock, perhaps. Not in the literal sense, but in the way that any machine has some rhythm, some pulse, some tick to it. Something steady, something consistent. But as soon as we start looking, the picture gets complicated. Because while humans build clocks to make sure every second is the same length as the last, the universe doesn't seem particularly concerned with that kind of consistency. It's worth starting with a very simple idea, the difference between time as we measure it and time as it might actually be. The clocks we build, after all, are human inventions. Every clock you've ever seen is built to match our definition of a second, which itself is just an agreement. It used to be defined by the rotation of the Earth, then later by the vibrations of a specific kind of atom. But that's still just us, choosing something regular and saying, this is what a second is. But imagine you're floating in space, far from Earth, far from anything human. Out there, there's no ticking, there's motion, yes. Planets orbit, stars spin, light moves. But none of it makes noise. There's no click, no beep, no hand sweeping across a dial, just movement and silence and scale. And yet we still feel, maybe instinctively, that the universe should have some kind of time. After all, things change, stars are born, galaxies collide, black holes grow, events unfold. There must be a before and after, even if we can't hear them. So maybe the real question isn't whether the universe has a clock in the way we picture a clock, but whether it keeps track of time at all. To even begin answering that, we have to look at what time is, and that's tricky, because the moment you try to define time, it slips away a little. Some physicists describe it as a dimension, like length or width or height, but with one key difference. We can only move forward through it. You can walk back and forth through space, but time, always forward, always one way. Others think of time as something more relational, that it's not a thing by itself, but a way of measuring change, a way of noticing that one state has become another. Think of a candle burning. You can say it's been 5 minutes because the wax has melted a little, or a tree's shadow on the sidewalk. It's moved slightly since you last looked. That's time too, not as a ticking, but as a sequence, as difference, as something that unfolds. From this perspective, the universe might not need a clock at all. The universe may simply be change. Every atom, every photon, every ripple of gravity, all of it shifting, rearranging, following its own laws. The idea of a clock might only arise when someone like us tries to measure that change. Still, there are parts of the universe that behave with a regularity that almost feels like a heartbeat. Pulsars, for example, the spinning remnants of collapsed stars, emit beams of radiation with astonishing precision. Some spin dozens or even hundreds of times per second, sweeping out a pulse that can be picked up across vast distances. These signals are so regular that we've actually used pulsars to keep time in certain scientific instruments. It's tempting to think of them as the universe's own clocks, lighthouses marking out the seconds in space. But they're not perfect. They slow down over time, they drift, they age. Even their near-perfect regularity is, in the long run, part of a larger cycle of change. On even grander scales, we can look at the expansion of the universe itself. Galaxies moving away from each other, light stretching as it travels through space, shifting toward the red end of the spectrum. This redshift gives us a kind of record, a way to estimate how long it's been since the universe began expanding. In that sense, the universe does seem to carry with it some memory of duration. Not a ticking exactly, but a trace. There's also entropy, the tendency for systems to become more disordered over time. It's not a clock in the traditional sense, but it does provide a direction, a sense of before and after. A cup shatters but doesn't unshatter, an egg scrambles but doesn't unscramble, and while this might not give us hours and minutes, it does point to something deeper, that the universe, whatever else it is, isn't static. It flows, not evenly, not predictably, but it flows. Still, none of this quite answers the original question. Does the universe have a clock? To answer that, we might need to go smaller, much smaller, down to the Planck scale, the smallest units of space and time that current physics can describe. According to some theories, time might not even be continuous. It might come in tiny, indivisible units. Planck time, each one about 5 times 10 to the minus 44 seconds. That's an unimaginably small slice of time. If that's true, then maybe the universe does have a fundamental clock, a tiniest possible tick, a rhythm baked into the quantum foam of reality. But even that is debated. Some theories suggest time isn't fundamental at all, that it's something that emerges only when systems grow complex enough to observe change, that below a certain level there is no time, only relationships, probabilities, and potential. In that view, time doesn't exist until it's experienced, which brings us to perhaps the most difficult part of all this, the idea that maybe time, and by extension clocks, are not part of the universe itself, but part of how we experience the universe. After all, time is deeply woven into how we live. Our brains are constantly anticipating, recalling, planning. We feel the passage of time not because the universe insists on it, but because we do. We experience change, we remember, we imagine, and so we measure. We built clocks because we are creatures who want to know when. When will the bread be done? When will the sun rise? When will I see you again? In that sense, maybe the universe doesn't need a clock. We are its clocks. Each of us, in our own way, ticking along, noticing change, telling stories about what came before and what might come next. Even now, as you listen, time is passing. Your body is keeping time, with your breath, your heartbeat, your neurons firing in soft cascades. Somewhere, A clock is counting the seconds of this video. Somewhere else, a star is flaring, a comet is tumbling, a planet is turning slowly toward its dawn. The universe continues, whether or not we measure it, whether or not we build clocks, whether or not we even look. And yet there is comfort in wondering, in asking questions that don't have simple answers, in sitting with the vastness and letting it settle around us. So let's stay with the question a little longer. Let's keep drifting. Let's follow the motion of light and the way stars seem to move in silence. Let's think about how ancient humans used the sky itself as a timekeeper, long before hours and minutes existed. Let's imagine for a little while longer what it might mean for the universe to keep time, or to simply be time, unfolding without pause. Somewhere between starlight and shadow, there are moments we rarely think about, not because they aren't there, but because they're too quiet to demand attention. These are the spaces between events, the stillness between signals, the calm drift between one galactic motion and the next. And yet, in their own way, these quiet stretches of the cosmos might tell us more about time than the burst of action ever could. Imagine floating in space, not in a spacecraft, not even in orbit, but out there, far beyond the planets, beyond the reach of any sun. You're just drifting in the vastness, surrounded by darkness, not because there's nothing, but because everything is so far away. Light from nearby stars doesn't flood the space. It's sparse, gentle, a distant glow rather than a beam. Now imagine you wait. You wait a second, then 10, a minute, an hour. Nothing happens, no movement, no sound, just space, just the moment. But is time still passing? It's easy to assume yes, that even in the absence of action, the second hand of some cosmic clock continues its journey. But what if there are no seconds out here? No reference point, no activity, no ticking? What if the concept of a moment only exists when something interrupts it? In everyday life, our sense of time is filled with anchors, words spoken, tasks completed, the shifting light of day. But in space, between stars, between gravitational pulls, between signals, there is only duration, nothing to mark it, nothing to count it. And this raises a gentle but persistent question. If there's nothing to change, does time move at all? This isn't a riddle. It's one of the genuine puzzles in physics. Time, as far as we understand it, is closely tied to change. The passage from one state to another, from full to empty, from before to after. But in a region of space where nothing interacts, where no particles bounce, no forces nudge, no radiation is absorbed or emitted, can we say that anything is happening? There's a thought experiment sometimes used in physics classes. It asks you to imagine a perfectly still universe, one where every atom is locked in place, every force is balanced, and nothing moves, no vibrations, no heat, no fluctuations. Would time still exist in that frozen tableau? Some would say yes. That time continues regardless of activity. That it's a fundamental background, a stage, as Newton suggested, on which everything else plays out. Others argue no. That time is a way of describing sequences, and without any sequence to describe, there's no need for time at all. Here on Earth, we don't get to experience that kind of stillness. Even in sleep, our bodies are in motion. Heartbeats, breathing, dreams stirring in the folds of the brain. Even when we're still, we're not still. But between stars, between galaxies, between the scattered wisps of gas and dust, there are places where stillness is almost real, where particles might travel millions of kilometers without encountering another, where nothing much happens for eons, and yet, from our perspective, those places have a history. The light that eventually reaches us, even if it took billions of years to arrive, tells a story with timing, a sequence, a before, an after. So maybe it's not that time doesn't pass between stars. Maybe it's just that nothing happens there to notice it. There's something unsettling about that idea. That time could stretch on endlessly without anything filling it. But maybe it's also comforting. Maybe those quiet stretches, those uneventful billions of years between galactic collisions, between supernovae, between the rise and fall of stars, maybe those are just as much a part of the universe's rhythm as the busy moments are. Think about music. Not just the notes, but the rest between them. The silence between piano keys. Those pauses are not interruptions. They are part of the pattern. Without them, the melody collapses into noise. Perhaps the universe works the same way. It has its crescendos, its chaotic bursts, its symphonies of motion. But it also has its rests, its long quiet moments, its negative space. And just like in music, the silence between stars might be telling us something, not through what happens in it, but through the fact that it's there at all. In astrophysics, we often measure time by light. Specifically, how long it takes light to travel from one place to another. Light is fast, about 300,000 kilometers per second, but space is big, very big. The distances between stars, even the ones closest to us, are measured in light years. That is, the distance light can travel in a year. And that's only the beginning. The nearest galaxy to ours, Andromeda, is about 2.5 million light-years away. That means the light we see from it tonight left. That galaxy when early humans were just starting to figure out how to make tools. So when we look at the stars, we're not seeing them as they are. We're seeing them as they were. Every point of light is a message from the past, and that alone is a kind of cosmic clock, not because it ticks, but because it measures delay. The light between stars is late, and that lateness tells us something about how far it's come and how long the journey took. But there's more. Between the stars, space isn't completely empty. There are tiny particles drifting, sparse but present. Hydrogen atoms primarily, some regions denser than others. These particles can absorb and emit radiation, and in doing so they reveal something about temperature, motion, even age. The way they interact with background radiation, that faint echo of the Big Bang, gives scientists a way to map the universe's history. Again, not a clock in the usual sense, but a record, a trace. The cosmic microwave background, often called the CMB, is one of the oldest things we can observe. It's a faint glow left over from when the universe was just a few 100,000 years old. And it's not uniform. It has tiny fluctuations, differences in temperature and density. Those fluctuations have been studied in detail, and they offer clues about the early conditions of everything, about how galaxies formed, about how matter began to clump together, about how time itself might have flowed differently back then. The fascinating thing about these observations is that they treat the universe not as a single object, but as something with age, with stages, with a timeline. And when we say the universe is about 13.8 billion years old, we're really saying that we found enough markers, enough events with durations and separations to build a calendar of sorts. A timeline written not in ink, but in light and temperature and distribution. So in that sense, maybe the universe does have a kind of clock, but it's not ticking uniformly. It's not synchronized. It's more like a record of waves, each overlapping the next. Stars flickering, then fading. Nebulae expanding, then thinning. Black holes devouring, then settling into silence. Each process with its own tempo. Even the expansion of the universe adds to this. Space itself is stretching, slowly but measurably. The rate of that expansion, called the Hubble constant, helps us estimate how long it's been happening. But this rate isn't fixed. It seems to have changed over time, faster in some epochs, slower in others, which raises new questions. If the rhythm of expansion varies, is there a fixed clock behind it? Or is the tempo of the universe something that evolves? Some cosmologists propose that time, as a whole, might be emergent, that it's not a backdrop but a byproduct of complexity. In this view, Time arises only when enough things exist to change in a coordinated way. Before stars, before matter, before interactions, maybe time had no meaning at all. Only when structure formed did the possibility of sequence begin. And this leads to an even subtler thought. Maybe time isn't something the universe has. Maybe it's something we assign to it, not incorrectly, not artificially, but as a way to make sense of what we see. We observe motion and change and distance and interaction, and we interpret those as happening in time. But perhaps time, like colour or sound or taste, is a kind of perception, a mental frame we use to organise experience, which doesn't make it any less real. It just means it might be more tied to perspective than to structure. Between stars, there may be no one to notice change, no one to mark a beginning or an end. But from here, from our tiny planet, from our orbiting clocks and reflective satellites, we see the distance between starlight and shadow, and we call that a moment, a slice of time. And maybe that's enough. Maybe the universe doesn't need to keep time on its own. Maybe the act of observing it, slowly, carefully from a distance, is what turns motion into meaning. And maybe those vast quiet spaces between stars aren't empty of time, but simply resting in it, waiting for someone to notice. When people first looked up at the night sky, they probably didn't think of it as a tool. It was more likely a source of wonder or mystery or even a kind of comfort. Something that was always there, always high, always dark, always filled with small cold lights, and yet, even without clocks, without measurements, without formal astronomy, the sky told stories. Not just myths and constellations, but actual stories about when to plant, when to hunt, when to expect the river to swell, or the frost to return. It was in its own quiet way a kind of calendar, a moving one, a shifting one, but a dependable one. The stars weren't just there for beauty, they were markers of change, markers of time. Long before we carved notches into bones or shaped dials into stone, people were using the movement of the heavens to orient themselves, not only in space, north, south, east, west, but in time. A certain star rising just before dawn might signal that a season was ending. A pattern of stars appearing overhead might mean it was time to travel or to stay put. Without needing numbers or instruments, the sky provided structure. This wasn't accidental. The Earth spins, and as it does, it presents different parts of the sky to the observer over time. It also orbits the sun, so the stars visible at night change slightly from week to week, month to month. It's a pattern so subtle you might not notice it unless you were watching carefully. But over many nights the changes add up, and those who watched long enough could see that the sky had a rhythm. The moon too offered a clock of sorts. Its phases are regular, predictable, from new moon to full and back again. Each cycle takes about 29.5 days. That rhythm doesn't depend on culture or language or technology. It simply is. A slow transformation written in reflected sunlight. So reliable, in fact, that many ancient calendars were based entirely on the lunar cycle. Still today, many religious and cultural observances are tied to the moon's phases, which means that even now, we still partly measure our time by the shape of a shadow on a distant surface. But beyond the moon and stars, something even more stable offers itself to observation: the motion of the sun, its rising and setting, its position in the sky at different times of the year. Early people noticed that the days grew longer or shorter depending on the sun's path. They saw that at certain points during the year, the sun would rise or set at the same location on the horizon, and these observations weren't lost. They were marked, carved into stones, aligned with structures, embedded in the layout of entire communities. Places like Stonehenge in England or the ancient observatories in Central America are aligned with solar events, solstices, equinoxes, the longest and shortest days of the year. These alignments weren't decorative, they were practical. They told people when the seasons would turn, when to harvest, when to prepare for winter, In this sense, the sky doesn't just contain time, it displays it. Openly, quietly, predictably. And yet, it does this without labels. There's no giant clock hand sweeping across the sky, no audible tick to separate 1 second from another. Just motion, just light, just repetition. But that repetition is enough. When we look at the sky today, we often do it through glass, through windows, through screens. Maybe we check an astronomy app. Maybe we watch a meteor shower forecast. Maybe we track a satellite. But it's easy to forget that the sky doesn't need interpretation. It interprets itself. The stars return to the same places. The planets wander in their slow looping paths. The constellations shift in and out of view. It all happens on a scale so large that, if we're not paying attention, we might think it's static. But it isn't. The changes are simply stretched out across time in a way that invites observation, not reaction. Even the word planet comes from a Greek word meaning wanderer, because compared to the stars, which hold their patterns, planets move, slowly, deliberately, but noticeably. Ancient astronomers watched them closely, tracked them, predicted them. Not because they were trying to understand gravitational fields or orbital mechanics, those concepts would come much later, but because they noticed that the sky was telling them something. A planet shifting from one constellation to another wasn't just a curiosity, it was a marker, a way of saying, this moment is different from the one before, and even now, with all our tools, all our precision, we still look up and see those same wandering lights. We still read time from their positions, even if we do it differently. Modern astronomy, of course, takes this much farther. With telescopes and data sets and mathematical models, scientists track the motion of celestial bodies with extraordinary accuracy. We can predict eclipses down to the second. We can map the positions of thousands of stars and project their locations years, centuries, even millennia into the future. This isn't because the universe is mechanical exactly. It's because the patterns are consistent. The laws that govern motion on Earth, gravity, inertia, momentum, apply to the stars as well. The same physics that makes a ball roll downhill also keeps the moon in orbit. And because those laws are stable, so is the sky. Not frozen, not unchanging, but stable in its logic, which makes it measurable. You can look at the sky and say, with some certainty, what the time is, not in hours or minutes, but in context. You can say, this is when that star rises, or the moon will be full tomorrow, or Venus is visible just before dawn. And all of those are statements about time, not human time, but sky time. Time measured not by devices, but by positions and angles and light. Even sunlight itself is a kind of measure. The light we feel on our skin, the brightness that wakes us in the morning, the shifting colours at dusk. All of it is time in motion. The Earth rotates. That rotation carries us from dark to light to dark again. And because it does so predictably, roughly every 24 hours, we build our schedules around it. The length of a day isn't arbitrary, it's planetary. It's literally written into the turning of the world, and yet even this isn't as precise as we might like to think. The Earth's rotation is gradually slowing, very slowly, but measurably. Over millions of years, the length of a day has changed. In the time of the dinosaurs, a day was a little shorter. In the far future, it will be longer. The moon, pulling gently at the oceans with its gravity, is slowly increasing the length of Earth's day by transferring energy away from the planet's spin. Which means that even the sky's clock isn't fixed. It changes, not wildly, not suddenly, but gradually, quietly. The sky measures itself, but it does so with a margin of error. That's where human tools come in. Atomic clocks, for example, measure time based on the vibrations of specific atoms. These are incredibly stable. So stable that over millions of years, they might be off by less than a second, and yet we sometimes have to adjust them. Leap seconds are occasionally added to account for the irregularities in the Earth's rotation, because while the Earth gives us a day, it doesn't always give us the same day. Not in exact terms. so we use tools to compensate. But the sky itself is still the original standard. It's not just Earth either. Every planet in our solar system has its own rotation, its own version of a day. Some spin faster than we do, some slower. Jupiter rotates in about 10 hours. Venus takes over 240 Earth days to complete one rotation. On some planets, a day is shorter than a night. On others, it's the opposite. And in each case, that rotation defines a rhythm, a local time, a sky-based clock that doesn't require batteries or networks or synchronization. In this way, the universe doesn't just have time, it displays it. And not in just one way, but in countless ways, through orbits, through rotations, through alignments and returns and disappearances. A comet streaking through the sky might take hundreds of years to return, but it will return, and when it does, it will mark a moment. It will remind us that time, however we define it, is still in motion, still unfolding. All of this brings us back to the original idea that the sky measures itself, not with digits or dials, but with consistency, with presence, with patterns that hold even as the light years stretch between them. We may build clocks to refine those patterns, to translate them into seconds and minutes, but the raw material, the cycles, the intervals, the repetition, is already there. So when you look up, even casually, even briefly, you're looking at something that has always kept time, not for our benefit, not by design, but naturally, automatically, continuously. You're seeing a measurement in progress, and whether you understand the names of the stars or not, whether you know the phase of the moon or not, whether you've read the equations or not, you're witnessing something ancient, something ongoing. You're seeing time not as a number, but as a position, as a glow, as a line that returns to itself again and again and again, and that, quiet, consistent, unscheduled, might be the most honest clock of all. It's easy to forget how recent seconds are. Not the phenomenon of time itself or the experience of change. Those have always been with us. But the idea that time could be divided into fixed, measurable units as small as a second, and that those units could be standardized, shared, tracked and scheduled, that idea is surprisingly modern. There was a time when no one on Earth had ever heard of a second. There was no need for it. Days and nights passed as full experiences, not as grids of equal moments. People lived by the sun, by the warmth, by the quiet return of familiar patterns. If time was counted, it was in the number of sunrises since something happened, or how many moons had passed, or whether the river had begun to rise again. Time, in that context, wasn't a matter of precision. It was a rhythm, a lived rhythm. When it was dark, you slept. When it was light, you worked. When the wind shifted, you listened. And if something took place during a certain phase of the moon, or when the stars returned to a certain part of the sky, that was enough to mark it. No clocks required. You can imagine a kind of clarity in that. A world where you knew what part of the year it was not because of a calendar pinned to the wall, but because the shadows in your village had changed, because the birds had returned, because the days felt different when you woke. The passage of time was less about division and more about attention, less about measurement, more about awareness. That kind of time doesn't disappear. It's still with us in quieter ways. We still notice the long evenings of summer and the crisp bite of autumn mornings. We still feel the shift when daylight lingers a little longer than it did the week before. Our bodies, even if we've filled our days with alarms and appointments, still respond to light, to seasons, to warmth and cold. Our internal clocks, though shaped by modern schedules, still whisper the old rhythms. But at some point humans wanted more than rhythms. They wanted consistency. They wanted to coordinate, to agree on when. The earliest attempts to measure time more precisely began with the simplest available change: shadows. A stick in the ground, catching the sun, will cast a shadow that moves in a predictable arc. That's the basis of a sundial, not because the stick knows the time, but because the Earth rotates and the sun's position changes. that change can be observed, marked, estimated, and even that gave people a kind of precision they hadn't had before. Still, sundials were local. They only worked in sunlight. They didn't divide time into hours or minutes. They simply gave a general sense of where the day stood. It wasn't until much later that people began to slice the day into parts. The ancient Egyptians divided daylight into segments, sometimes 12, though these segments varied in length depending on the season. An hour in summer was longer than an hour in winter, because what mattered was the structure of the day, not the equality of the parts. Water clocks came next, containers that dripped or poured at a steady rate, marking time not by celestial movement but by flow. Some were quite sophisticated, with dials and floats and gears, but still, the focus was on portions of the day, enough to ring a bell, to announce a prayer, to keep some order. Minutes weren't yet necessary. Seconds were still far away. Mechanical clocks began to appear in Europe in the Middle Ages. These were heavy, complex devices driven by weights and regulated by escapements, gears that released at regular intervals. At first, they didn't even have faces. They didn't need them. Their job was to chime the hours. That was enough. Hearing the bell was the cue. Time was something you listened for, not watched. Eventually, as technology improved and clocks became more reliable, people added hands to show the hour. Then, as mechanisms became more refined, they added minute hands. And finally, with the invention of the pendulum clock in the 17th century, seconds arrived. Not because daily life demanded them, but because the technology allowed it. For the first time, people could track time in small, equal pieces. Not vague intervals, not approximate durations, but consistent, measurable units. A second became not just a concept, but a visible slice of time sweeping past on a dial. And once it was visible, it became hard to ignore. The second is defined today by the vibration of cesium atoms, 992,631,570 cycles per second to be exact. But that definition only came after centuries of approximation. Before atomic time, a second was 1/86,400th of a day. That is one part of a day divided into 24 hours, each with 60 minutes, each with 60 seconds. The numbers feel arbitrary until you realize they came from ancient systems. The sexagesimal base 60 system used by the Babylonians, whose influence lingers in every watch and clock. The choice to divide time into these units wasn't inevitable. It was a decision, a framework built on earlier systems, carried forward because it worked well enough. And over time, as the need for precision increased, the definitions became more exact. Today, timekeeping is astonishingly accurate. The best atomic clocks would drift less than a second over the entire age of the universe, and yet, for most of history, that level of precision would have been meaningless. You didn't need seconds to milk a cow. You didn't need nanoseconds to track a sunrise. Those units only became useful, or necessary, as society developed technologies that demanded synchronization. Railways, for instance, made standardized time essential. Before trains, each town kept its own local time, based on the position of the sun. Noon was when the sun was highest overhead, but that meant time differed slightly from one place to another. A train running from one city to another had to reconcile these differences, and so time zones were introduced, standard time was adopted, and seconds, once a luxury of the clockmaker, became part of the public schedule. Today, seconds govern far more than we notice. They're behind the timing of satellites, the coordination of communication systems, the synchronization of financial transactions. They're embedded in the protocols that allow devices to talk to each other, in the timing of signals that guide planes and ships. Our modern infrastructure depends on shared, stable time. And yet, when you walk outside and look at the sky, none of that is visible. The stars don't blink on the second. The moon doesn't rise on a schedule. The clouds don't consult a clock. They move according to their own timing. Not random, but not measured in even slices either. That tension between the way nature behaves and the way we measure it is part of what makes the idea of a second so strange. It's a human idea, useful, necessary in some cases, but not something the universe appears to need. There's no evidence that time itself is naturally divided into seconds, or minutes, or hours. These are frameworks we've built to manage complexity, to coordinate lives, to create expectations. They help, but they're not fundamental. If you step away from clocks, if you ignore the beeps and alerts and blinking digits, you'll find that time feels different. It expands or contracts. It slips by unnoticed, or it stretches across long, empty afternoons. That's because the second isn't how we feel time, it's how we count it. What we feel is change, emotion, memory, anticipation. Those things aren't bound by equal slices. They drift, they clump, they fade and intensify in unpredictable rhythms. That's why moments can feel longer than minutes, and hours can vanish in conversation. The second might tick, but our experience of it doesn't always match. Still, the second is part of our world now. It regulates traffic lights. It guides rocket launches. It governs heartbeats in operating rooms. It times athletes in Olympic finals. It ticks away in devices we forget are even there. It's in our wrists, our walls, our screens, our phones. And while we may not think about it often, it's a constant companion. A reminder that, even as we live in flowing, uneven moments, there is a grid underneath, a structure, a measurement waiting to be acknowledged. But long before any of that, before pendulums, before gears, before dials, people lived in time that was felt, not counted. Days came and went, nights passed, seasons turned, and that was enough. So while the second is precise and useful and deeply embedded in modern life, it's not the only way to understand time, it's not the original way, and it may not be the ultimate way either. There may be other rhythms waiting to be noticed, other pulses, other patterns, not counted but lived. When we think about motion in the universe, we often picture planets orbiting stars, or moons circling planets. These are the kinds of movements that feel familiar. They're close enough to imagine. We can see the moon rise and set. We can observe the sun moving across the sky. We've learned to understand those rhythms. But once you move beyond those local systems, things become more abstract, larger, slower, less immediate, and yet they move too. If you pull back far enough, beyond our solar system, beyond the Milky Way, what you begin to see is structure. Not just stars scattered randomly through space, but large-scale patterns, systems orbiting within larger systems, clusters of galaxies, superclusters stretching across unimaginable distances, and within each galaxy a central core, stars spiraling around that center, not chaotically, but in motion that follows a gravitational shape. At that scale, it becomes hard not to draw comparisons to machinery. Not because the universe is mechanical in the human sense, but because the motions are so consistent, predictable, patterned. Galaxies rotate, not like wheels, but like vast gravitational whirlpools, each star tracing its path, influenced by the mass around it. And while these motions aren't uniform, stars closer to the centre of a galaxy move at different speeds than those farther out, there is still a rhythm to it, a dynamic balance, a movement that, over millions or billions of years, creates something close to stability. In that way, it's tempting to imagine galaxies as gears in some enormous invisible mechanism, each turning at its own pace, each interacting with others through gravity, through momentum, through the subtle influence of mass on space itself. But if they're gears, they're not gears in a clock that counts seconds. They're gears that turn over cosmic durations, thousands, even millions of years per rotation. One complete spin of our own galaxy takes about 230 million Earth years. That's how long it takes for the Sun, along with its planets, to make a full journey around the Milky Way centre. Which means that everything we know, every recorded human event, every written history, every city built and destroyed, All of it has happened during a tiny fraction of one galactic rotation. We haven't even completed a single turn yet. And still, the galaxy turns. It always has. That movement, though too slow to perceive, is part of what defines the environment we live in. The shape of our solar system's path through the galaxy affects our exposure to cosmic rays. The density of nearby stars can shift over time. Even distant gravitational influences can subtly affect the structure of our planetary system. So while we might not feel the galaxy's rotation, it is happening beneath us, around us, through, just as the Earth spins under our feet unnoticed, the galaxy turns beneath our solar system, sweeping it along in a spiral that's both constant and almost invisible. If you look at images of galaxies taken through telescopes, what you'll often see is that spiral structure, arms sweeping outward from a glowing core. Those arms aren't solid structures, they're density waves, regions where stars are more tightly packed, where new stars are forming. They persist not because stars are glued together, but because the gravitational dance of the galaxy keeps pulling them into these sweeping forms. It's a shape born of motion, maintained by gravity, stabilized over immense time spans, and like all gears, galaxies interact, not mechanically, but gravitationally. Sometimes galaxies collide. These collisions aren't like crashes in the human sense. The space between stars is so vast that, even in a galactic merger, most stars pass by each other without touching. But the gravitational effects are dramatic. Stars can be flung into new orbits. Gas clouds can be compressed, triggering new bursts of star formation. Structures warp, spiral arms distort. The cores of the galaxies may eventually merge, forming a new, larger galaxy. These interactions can take hundreds of millions of years to play out. They're slow, enormous, transformative, and they happen all the time. Our own galaxy is currently on a collision course with the Andromeda Galaxy. They're still about 2.5 million light-years apart, but they're moving toward each other. In about 4 billion years, the two will begin to merge. Over another few billion years, they'll form a single, larger elliptical galaxy. We won't be around to see it, but the motion is already underway. It's not something we can stop, or accelerate, or delay. It's just part of the large-scale rhythm of the universe. And that brings us back to the idea of time, because in all these motions, the rotations, the mergers, the slow restructuring of space, what we're seeing isn't time in the clock sense. We're seeing time as change, time as motion, time as the unfolding of gravitational consequences. There are no ticking seconds in a galaxy, but there are turns, there are trajectories, there are outcomes that follow causes. A galaxy doesn't need a stopwatch. It follows the laws of motion, not because it's trying to, but because it has no choice. The stars move because the mass of the galaxy curves space in a certain way. The motion is a response, not a goal. Still, when we observe these motions, we translate them into time. We say a galaxy rotates every so many million years. We estimate the age of star populations. We trace chemical signatures to determine when stars formed, when they died, when they scattered their elements into space. In that way, galaxies do more than move. They keep a kind of record. Stars carry the story of their environments. Their composition reflects the material available at the time they formed. Older stars tend to have fewer heavy elements. Newer stars, born from recycled material, enriched by generations of supernova, contain more. By studying the light from these stars, we can estimate their age, their placement, their origin. So while galaxies don't mark time deliberately, they contain time, encoded in structure, in motion, in light. Even the black holes at the centers of galaxies, those mysterious massive objects, play a role. They don't just sit still. They influence the movement of stars around them. They shape the behavior of the galactic core. Some even emit jets of radiation powered by material falling in. These signals travel across space, marking activity that may have taken place millions of years ago. And we see them now, not because they happened recently, but because the light has finally reached us. Every galaxy is a machine of sorts, not made of gears, but of gravity, not driven by springs or circuits, but by mass and motion. They don't tell time with regular beats, but they show time. They show what has happened, what is happening, and what will happen. We use these motions to build models, we run simulations, we try to understand the structure of the universe by comparing real observations to theoretical predictions. And through this process, we begin to see that even on these massive scales there is consistency. A galaxy doesn't behave randomly. It behaves according to known rules, rules we can test. And while we may not be able to predict every detail, we can predict patterns. We can see how structure emerges, how systems evolve. In that way, galaxies are not clocks, but they are processes, and processes, by definition, unfold over time. Whether we count that time in seconds or years or rotations or cycles, the effect is the same. The universe changes, not quickly, not loudly, but steadily. And every galaxy we observe is a record of that. A spiral of memory, a wheel turning slowly through space, a reminder that even at the larger scales, time is never still. If you were to remove everything else from the universe, the planets, the stars, the galaxies, the dust, even the background hum of microwave radiation, if you could somehow sweep it all aside, what would remain is not silence, not emptiness, but something still deeply active. Light. Not the light we normally see, the kind that reflects off surfaces, or warms the skin, or helps us read late into the night, but light in its broader, deeper sense, as a form of energy, as a messenger, as something that moves not because it chooses to, but because it must. Light doesn't rest, it doesn't slow down, and it doesn't pause between destinations. It just moves at exactly the same speed, always, through vacuum, through space, through time. That consistency, that exact pace of travel, is not just a feature of light. It's a defining property of the universe. The speed of light is not simply fast, it is fixed. It is built into the very equations that describe how reality operates. In physics, it serves as a constant, not just in measuring how fast light travels, but in shaping how time and space relate to one another. And in that way, light is more than energy. It is structure, it is reference, it is rhythm. It doesn't tick like a clock, but it paces the universe. When a photon, a particle of light, is emitted from a source, it travels outward at that exact speed. It doesn't lose momentum, it doesn't forget its origin, and if nothing interferes with it, it will continue travelling indefinitely. That distance and the time it takes becomes a kind of record, a built-in delay, a traceable signature of when and where the photon came from. This is how we see the universe. Not as it is now, but as it was. Because all the light we observe has been in motion. Even sunlight takes time to reach us, about 8 minutes from the surface of the sun to our eyes. The starlight we see at night may have taken decades, centuries, even thousands of years to arrive. In many cases, the source of that light no longer exists in the form we see it. A star may have collapsed. A galaxy may have shifted. But the light keeps coming, long after the event. This isn't just poetic, it's physical. The delay in light's arrival gives us a window into the past, a quiet, constant stream of ancient information. Light has no awareness, of course. It doesn't know it's travelling. It doesn't choose its direction. It simply obeys the laws that govern all things in motion. But in doing so, it becomes something remarkable, a natural time capsule, one that doesn't preserve an object, but a moment, a snapshot of energy frozen in transit. This is why telescopes are not just tools of magnification, but tools of time. When astronomers look deeper into space, they are not just seeing farther, they are seeing earlier. Each photon collected is a piece of history, a silent trace of an earlier event. The deeper the telescope sees, the further back in time it looks. The James Webb Space Telescope, for example, is observing light from some of the first galaxies that ever formed. Light that has travelled across the expanding fabric of space for over 13 billion years. Not because those galaxies are moving fast, but because the universe itself has stretched in the time it took their light to reach us. And that stretching, called redshift, is a kind of cosmological timestamp. As space expands, the wavelength of travelling light stretches with it. What began as ultraviolet becomes visible. What began as visible becomes infrared. The colour of the light shifts, not because of motion through space, but because the space itself is changing. We can measure that shift. We can compare the light's original profile to what we observe now. And from that, we estimate how long the light has been travelling, how much the universe has expanded, and in turn how old the source might be. In this way, light doesn't just carry images, it carries timing, it carries distance, it carries the echo of duration, it tells us when, not in seconds, but in accumulated delay. And in doing so, it reveals the rhythm of the universe, not the heartbeat of matter, but the silent, steady drumbeat of photons arriving, one after another from every direction. Even now, the light hitting your skin, from a lamp or a screen or the night sky, has a journey behind it. Most of that journey is incredibly brief by cosmic standards. But it's a journey nonetheless, a movement, a passage. And that passage, when scaled up across millions of sources, becomes a pattern. It becomes time. Light behaves with extraordinary regularity. In quantum mechanics, photons are described as both particles and waves. They oscillate, they vibrate at specific frequencies, and those frequencies, like notes in a song, are exact. This is how atomic clocks work. By measuring the oscillation of light emitted by electrons shifting between energy levels in atoms, usually cesium or rubidium, we can define time with extraordinary precision. Not because we impose a rhythm, but because the rhythm is already there, embedded in the nature of the atom and in the behaviour of light itself. These oscillations are stable, reproducible, and because of that, they've become the standard by which we define the second. So in a very real sense, light sets the pace for our most precise clocks. But the irony is that light itself doesn't experience time. According to relativity, time slows down for objects as they approach the speed of light, and at the speed of light, exactly 792,458 meters per second. Time, in the reference frame of the photon, halts completely. This doesn't mean light is frozen, it moves, but from the photon's own perspective, if it had one, the journey is instantaneous. No time passes between emission and arrival. Of course, photons don't have perspectives. They don't have awareness. But the physics is still telling us something strange. That even though we use light to measure time, light itself does not age. It does not experience before or after. It simply exists at the edge of time, always in motion, never waiting. This creates an interesting contrast. On one hand, we rely on light to define and detect time. We use it to build clocks, to observe cosmic history, to coordinate our instruments and our communications. But on the other hand, light itself exists in a kind of timeless condition, always in motion, never at rest, never aging. That dual role, both as the measurer of time and the inhabitant of timelessness, makes light unique. It is both the record and the medium, both the clock and the exception. When we talk about the silent rhythm of light, we're not describing a beat we can hear. There's no sound in space. There's no ticking. But the rhythm is still there, in the precision of light's properties, in its consistency, in its unbroken path, and that rhythm plays out all around us, in lasers guiding data across oceans, in fibre optics carrying information at nearly light speed, in the GPS satellites triangulating our position based on precisely timed pulses of light between orbits and Earth. Without light, we would lose not just illumination, but coordination. orientation, context. We would lose the ability to see not only where we are but when we are. The sky would still exist, the stars would still burn, but we would not see them. Not because they vanished, but because their messages never arrived. So when you look at a star, or a planet reflecting sunlight, or even the soft glow of a screen in the dark, what you're really seeing is timing. Not the time marked on a clock face, but the moment of arrival, the product of a journey, the conclusion of a process that began somewhere else, in a fusion core, in an atom, in an electron, and ended here. And that arrival, that presence, is part of a larger pattern, not a beat, not a tick, but a constant, a movement that defines the structure of space and the passage of time. Even though light is silent, its rhythm is not hidden. It's in every image we capture from a telescope, in every measurement we take from a distant star, in every reflection, every shadow, every rainbow. It is not just what we see, it is how we see, and in seeing, we begin to measure, not because we built the rhythm, but because we learned how to recognize it. If you listen carefully enough to the universe, not with ears but with instruments tuned to radio waves, you might notice something strange, something regular, a signal that doesn't drift, doesn't fade, doesn't flicker randomly, but pulses, over and over at perfectly spaced intervals, like a cosmic heartbeat, steady, predictable, persistent. These signals aren't made by machines or messages from distant civilizations. They're natural, emitted by objects so dense, so extreme, and so precisely timed that they've earned a fitting nickname, pulsars. In many ways, pulsars are some of the most reliable timekeepers in the known universe, not because they were designed to be, and not because they're measuring anything in particular, but because of how they're built, what they are, how they behave. A pulsar is a kind of neutron star, the collapsed core left behind after a massive star explodes in a supernova. When a star reaches the end of its life and runs out of fuel, it can no longer support itself against gravity. If the star is massive enough, the collapse is catastrophic. Its core is crushed into something unimaginably dense. Atoms themselves are squeezed beyond recognition. What's left is a sphere about 20 kilometers across, roughly the size of a city, but with more mass than our entire sun packed inside it. That density does something interesting to physics. It creates a magnetic field trillions of times stronger than Earth's. It also spins fast. The conservation of angular momentum means that when a massive object collapses inward, it rotates more rapidly. It's the same principle behind a figure skater pulling in their arms to spin faster. But in the case of a neutron star, the result is rotation so fast, so intense, that the object becomes a kind of cosmic beacon. Beams of electromagnetic radiation shoot out from the pulsar's magnetic poles, and if those beams are aligned just right, sweeping past Earth like a lighthouse beam across a dark ocean, we detect a pulse. Not once, not occasionally, but repeatedly, with extraordinary consistency. Some pulsars spin once every second, others hundreds of times per second. The fastest known pulsars rotate over 700 times a second. That's more than 40,000 revolutions per minute. Each rotation produces a pulse, and those pulses arrive at Earth like clockwork. When pulsars were first discovered in 1967, the regularity of the signals was so unexpected that the researchers briefly considered the possibility of artificial origin. They labelled the signal LGM-1, short for little green men. But as more pulsars were found, and their properties became better understood, it became clear that these were natural phenomena, no less extraordinary for being unintentional. They weren't broadcasting on purpose, they were just spinning. And yet, the precision was undeniable. These pulses are so stable that scientists have used them as timing references, similar to atomic clocks. Some pulsars are so consistent that they rival the accuracy of human-made timekeeping devices, and because their signals come from far beyond Earth, they offer something our local clocks can't: independence from terrestrial systems, a kind of universal timestamp. This is why pulsars have been proposed as part of a galactic positioning system, an interstellar version of GPS, using pulsars as fixed reference points scattered across space. By comparing the timing of pulses from several known sources, a spacecraft could, in theory, determine its location anywhere in the galaxy. No need for satellites, no need for Earth-based signals, just the rhythm of the universe quietly guiding the way. But beyond their practical applications, pulsars offer something more fundamental. They represent one of the clearest examples of natural regularity on cosmic scales. In a universe filled with chaos, with collisions and expansions and entropy, pulsars give us a kind of order, not perfect order. Over long periods, pulsars slow down. They lose energy. Their rotation decays. The pulses become slightly less frequent. But these changes are so gradual, so well understood that they can be predicted, accounted for. Even the irregularities become part of the pattern. Some pulsars exhibit glitches, sudden tiny speed-ups in their rotation. These are thought to be caused by shifts in the neutron star's interior, perhaps interactions between a superfluid core and the crust. Even here, in the most stable of systems, the universe reminds us that no rhythm is eternal. But the changes are measurable, trackable. They follow rules. In this way, pulsars are not clocks in the traditional sense. They don't measure time by counting. They don't have gears or pendulums or vibrating atoms, but they create intervals. Predictable, observable intervals. And those intervals become useful. They allow us to map the passage of time from outside the human framework. Not by ticking off seconds, but by watching the dance of radiation from a city-sized object spinning faster than anything we can imagine. There's something humbling about that. To think that a collapsed star, something born in fire and destruction, can become a steady signal in the dark, a marker, a rhythm, a kind of beacon, and the universe is full of them. We've discovered thousands of pulsars, some in isolation, some in binary systems where they orbit another star, some so regular that they're used to test the predictions of general relativity, measuring tiny shifts in timing caused by gravitational waves or orbital decay. In one remarkable case, scientists found a pulsar orbiting a white dwarf. The system's timing was so precise that it allowed researchers to detect the influence of gravitational waves, ripples in space-time, affecting the orbit ever so slightly. Not directly observed, but inferred from timing, from the beat of a distant dead star. In another case, a pulsar was discovered with planets orbiting it, the first confirmed detection of exoplanets. They weren't Earth-like. The environment was harsh, bombarded by radiation. But the planets were real, and their presence was detected not by seeing them, but by noticing tiny variations in the pulsar's rhythm as the planets tugged on it. That's how sensitive these cosmic metronomes can be. Even tiny changes in mass, in position, in gravity. They all leave signatures in the pulses, and we can read those signatures, not quickly, not easily, but reliably. Each pulse is like a drumbeat from the edge of known space, not made to be heard, but there nonetheless. And while pulsars don't tell time the way a wristwatch does, they show that time, or at least intervals, can be written into matter itself, into spin, into radiation, into patterns that persist not for minutes, but for millions of years. They remind us that timekeeping doesn't always need intention. Sometimes it's a byproduct of physics. Spin a dense object. Let its magnetic field sweep a beam of light across the void. And if you're lucky enough to be in the path of that beam, you'll see a pulse, then another, each one arriving on schedule as if the universe itself was keeping track. But it isn't exactly. The universe isn't counting, it isn't scheduling, it isn't ticking toward anything. It just is. The pulses happen because the laws of motion and magnetism and radiation say they must, no clockmaker, no goal, just matter and energy behaving as they do. And yet, from that indifference, we find rhythm. We build models, we make calendars, we chart orbits and measure gravitational waves. We take a collapsed star spinning alone in the dark and turn its pulses into knowledge. And if that doesn't make it a kind of clock, it at least makes it something better, a natural pattern, one that doesn't require winding or electricity or maintenance, one that will continue long after the lights in our cities have dimmed, long after our calendars have lost their pages, just a signal, a steady beat. There's a particular comfort in knowing that out there, beyond the atmosphere, beyond the noise of Earth, something is still turning, not because it has to, not because it wants to, but because the laws of nature made it that way, and in those quiet, relentless pulses, there is a kind of peace, not human peace, but the peace of physics, the peace of something that simply continues, no questions asked, no answers needed. Far beyond the stars we can see, past the galaxies with their spiralling arms and brilliant cores, beyond even the reach of the fastest pulsars, there's something quieter. It doesn't flash, it doesn't spin, it doesn't pulse in neat intervals, and yet it's everywhere, filling all of space, not as a bright light, but as a faint glow, cold, uniform and ancient. This glow is not a reflection of anything nearby. It isn't starlight bounced off dust. It isn't the residue of solar radiation or the breath of nearby quasars. It is something far older, something that comes from a time before stars existed, before galaxies formed, before there was anything you'd recognize as structure at all. It's called the cosmic microwave background, often abbreviated as CMB, and it's one of the oldest signals in the observable universe. But despite its age, it isn't a whisper of silence. It's a timestamp, a moment frozen in light, a relic of the very earliest time that could be seen. To understand where this light comes from and why it matters, you have to go back. Not centuries or millennia, not even millions of years, but nearly all the way, about 13.8 billion years into the past. That's how long the universe has been expanding since what we call the Big Bang. In its earliest moments, the universe was not the dark, silent place we see when we look up at night. It was dense, hot, opaque, a plasma of charged particles and light so tightly packed that photons couldn't travel freely. Every bit of energy was colliding with something else. Atoms hadn't formed yet. There were no boundaries, no transparency. It was more like looking inside a glowing fog than looking out into space. But over time, that fog began to cool. As the universe expanded, its density dropped, and after about 380,000 years, a blink, cosmologically speaking, the temperature fell low enough for electrons to combine with protons. These combinations formed the first neutral hydrogen atoms, and when that happened, the fog lifted. This period is known as recombination, and it marks the first time that light could travel freely through space. No longer constantly scattered by charged particles, the photons released during this moment began to stream outward in all directions. They've been travelling ever since. That light is the cosmic microwave background. It's not particularly bright now. In fact, it's so faint that it wasn't detected until 1965, when two radio astronomers stumbled across it while working on a different project. They found a persistent noise, a background signal that didn't go away no matter where they pointed their antenna. At first, they thought it was interference, maybe a technical issue, maybe pigeon droppings inside the equipment. But even after cleaning everything and ruling out every known source, the signal remained. What they'd found was the afterglow of the Big Bang, light that had been travelling, uninterrupted since nearly the beginning of time. Today that light is stretched. The universe has expanded enormously since it was first released, and the energy of the photons has been redshifted into the microwave region of the spectrum. Much lower energy than visible light, but it's still there, uniform, filling space. with a temperature of about 2.7 Kelvin, just a few degrees above absolute zero. This temperature isn't random, it's a record, a remnant, a measure of how much the original light has cooled as space has stretched. And that makes it a kind of cosmic clock. Not because it ticks, not because it changes from moment to moment, but because it carries within it the memory of when it was created. When we observe the CMB, we're not seeing something nearby. We're seeing something distant in both space and time, a sphere of light coming from every direction, representing the edge of the visible universe, not in terms of distance, but in terms of time. Everything inside that sphere is younger, everything beyond it is hidden, because no light from there has had time to reach us yet. In this way, the CMB defines the observable boundary of the universe. It's not a wall, it's not a surface, it's a moment recorded in radiation, and that moment gives us something rare, a universal reference point, a fixed event, a time when conditions across the universe were roughly the same. From there, we measure everything else, the age of stars, the formation of galaxies, the structure of space itself. But the CMB isn't perfectly smooth. If it were, it would still be valuable, but much less informative. What makes it truly important is that it contains tiny variations, slight differences in temperature and density from point to point. These variations are incredibly subtle, on the order of 1 part in 100,000, but they are essential. They show that the early universe wasn't completely uniform. There were tiny fluctuations, areas slightly denser or cooler than others, and those tiny differences would grow under gravity to become everything we see today. Galaxies, clusters, stars, planets, us. By studying the exact patterns in these fluctuations, their size, their distribution, their intensity, scientists can learn a great deal about the early universe, about its composition, its shape, its rate of expansion, even the amount of dark matter and dark energy it contains. These aren't guesses, they're measurements. Measurements made by observing the frozen pattern of a moment that is never repeated. In that sense, the CMB is more than a timestamp. It's a fingerprint, a record of the universe at the moment it became visible. Not because it was trying to say anything, but because light, once released, remembers. The data collected from satellites like COBE, WMAP and Planck have mapped the CMB in extraordinary detail. The resulting images don't show stars or galaxies. They show temperature, warm patches, cool patches, in a pattern that's both random and informative. From those maps, cosmologists have built models of how structure formed, how the early fluctuations grew into filaments of matter, how those filaments seeded the cosmic web, how the universe, from a hot, nearly featureless plasma, became the diverse and complex place we now observe. All from a silent glow, a snapshot stretched across the sky. There's something extraordinary about that. We don't usually think of light as a source of stability. It moves, it flickers, it's here, then gone. But in this case, light has endured, not as an image or a beam, but as a presence, a texture, a background hum that reaches us from every direction. It has no direction of origin because it comes from all directions equally. It's not being produced anymore, it's simply arriving. And each photon, each tiny packet of energy, carries with it the timestamp of an ancient release. We use that timestamp not just to mark the beginning of what we can see, but to anchor our understanding of time itself. From that moment outward, time begins to take shape. Not time as an abstraction, but time as a sequence of events, moments following moments, light leading to stars, stars leading to elements, elements leading to planets, planets leading to people who build instruments and detect radiation and ask questions about what it all means. The CMB doesn't change, it just is. A signal from a time when the universe was still soft and glowing. Not because we remember it, but because the light does, and in that light we see a kind of certainty. Not the certainty of answers, but the certainty of presence, of continuity, of something that began and never stopped moving. So while clocks on Earth tick away seconds and watches mark the hours and pulsars beat out millisecond intervals, the cosmic microwave background does something else entirely. It endures, it spans, it holds, and in doing so, it reminds us that the universe doesn't just have moments, it makes them, preserves them, carries them forward, not for our benefit, but because that's what energy does in a universe where time flows forward. And in the glow of that ancient timestamp, we find our earliest measurement, the first moment that could be seen, and everything after, every star, every orbit, every signal follows in its light. If you were to imagine space as something fixed, a stage, a backdrop, a surface on which matter moves, you might picture the stars and galaxies drifting slowly across a vast, unchanging expanse. Planets orbiting suns, suns spinning through galaxies, galaxies sweeping along in great arcs. All of it happening within space, but not to space. That image, though comforting, isn't quite right, because space doesn't just hold the universe, it stretches with it. Space itself is dynamic, not in the way wind is dynamic or water or flame. It doesn't swirl or ripple in any familiar sense, but it changes, quietly, continuously, all the time. This change, the expansion of the universe, isn't something we notice in daily life. It doesn't tug on our bodies or shift the ground beneath us. The space between objects bound by gravity, like planets or solar systems, remains essentially constant. Your coffee cup doesn't get farther away from your hand. The moon doesn't drift from Earth because of expansion. Gravity holds those systems together. But when you look beyond gravitationally bound systems, beyond our solar system, beyond our galaxy, you start to see something else. Galaxies not just moving, but receding. The farther away they are, the faster they seem to be going. This isn't motion through space, it's the stretching of space itself. That observation was first made in the 1920s by Edwin Hubble, though others had hinted at it before. He noticed that distant galaxies were redshifted. Their light stretched toward the longer, redder wavelengths of the spectrum. This redshift wasn't a Doppler shift caused by actual movement through a fixed medium. It was the result of space expanding as the light travelled through it. The wavelengths themselves were elongated, not because the galaxies were flying away through space, but because the space between us and them had stretched. This realization changed everything. It meant the universe wasn't static. It wasn't eternal and unchanging. It had a history, a direction, a tempo, and that tempo, though silent, is everywhere. It's in the gap between galaxies. It's in the time it takes light to arrive. It's in the glow of the cosmic microwave background. The expansion of space isn't something we can hear or touch, but it's measurable. It has a rate, a parameter known as the Hubble constant. This constant tells us how fast the universe is expanding at different distances, or rather, how much space stretches per unit of time for every megaparsec, every 3.26 million light-years of separation. The numbers vary slightly depending on how we measure them, and there's still some tension between different methods of calculation. But the general picture is clear. The universe is expanding, and it has been since the moment of the Big Bang. It's not expanding into anything. There's no edge, no outside. Space isn't growing like a balloon inflating into a room. The balloon is space. The surface of it, the geometry, is what's changing. And all the galaxies are on that surface, not moving through it, but carried by it. The scale of this expansion is almost beyond comprehension, and yet it defines the structure of time itself, because as space expands, light must travel farther to reach us, not just in distance but in duration. A photon emitted shortly after the Big Bang has been stretched and delayed and redshifted by billions of years of expansion. Its journey isn't just long, it's evolving as it unfolds. In that sense, the expansion of the universe creates a slow, deep rhythm. Not a beat, not a clock, but a change, steady, continuous, inescapable. It's not something we notice from moment to moment. You could wait your entire life and never directly observe space getting larger. But over cosmological timescales, the effect is dramatic. Galaxies that were once visible become too distant to see. Light that once reached us no longer can. Even the cosmic microwave background, that ancient wall of first light, is drifting farther away. Not because it's moving, but because space is. This slow thrum, this stretching of the cosmic fabric, is not uniform in its influence. It acts most noticeably where gravity is weakest. Within galaxies, within solar systems, gravity binds matter together tightly enough to resist expansion. But between galaxies, in the vast dark voids of intergalactic space, the stretching is unopposed. There, space thins like taffy being pulled, smooth, silent, unrelenting. This kind of change doesn't come with alarms. It isn't noisy, but it accumulates. It alters the background against which all cosmic events take place. In the early universe, matter was tightly packed. Galaxies were closer together. Interactions were more common. But as expansion continued, that density thinned. The structures we see today, clusters, filaments, voids, emerged not in a static environment, but in one that was constantly growing. And that growth shapes our understanding of time. Because the universe wasn't always like this. It was denser, hotter, brighter, and it will not always be like this. It will continue to stretch. What that means for the far future is a matter of physics and speculation. If the current rate of expansion continues, galaxies will recede beyond our ability to detect them. The universe will grow darker, colder, lonelier. Not because things are disappearing, but because they are being carried beyond the cosmic horizon, the limit of what light can reach us. If the expansion accelerates, as current data suggest it is, driven by something we call dark energy, that process will happen faster. More galaxies will vanish from view. More light will fail to arrive. Over trillions of years, the observable universe may contract not in space, but in content. The volume we can see will remain, but what it contains will shrink. Not because matter is disappearing, but because time is drawing it out of reach. And yet the rhythm of expansion continues. Not as a clock you can hold, but as a change you can track. There is elegance in that, not in how it looks, but in what it tells us. That the universe is not fixed, that time is not an illusion, that change is real and measurable and written into the fabric of existence. We tend to think of expansion as a function of space, but it is equally a function of time. Without time there would be no change, no redshift, no stretching of light, no movement of galaxies from one relative position to another. Time and expansion are intertwined. One makes the other visible. We see time through expansion, and we measure expansion through time, and that measurement is not abstract. It's in the photons we receive from distant objects, in the shape of the cosmic web, in the cooling of the background radiation, in the fading of starlight. The slowness of it, the scale, makes it easy to miss. But it's always there. The pace of everything else is layered on top of it. The rotation of planets, the orbit of moons, the rhythm of atomic clocks. All of it occurring inside a universe that is, at every moment, growing larger. Even the silence of that expansion is a kind of signal. Not one we can hear, but one we can calculate, observe, anticipate. It defines the framework of what's possible, how long it takes to send a signal, how much time passes before a message returns, how the past remains visible or doesn't. And though it has no sound, no pulse, no vibration, the expansion of space is perhaps the most constant rhythm we know, not imposed, not maintained, but inevitable. So when you look up at the stars, the ones still close enough to see, you're looking into a moment already shifting, not because the stars are running away, but because the space between is stretching. Slowly, immeasurably in human terms, but relentlessly. And that slow thrum, that almost imperceptible tempo, is the beat behind everything else. When we think about time, especially on a day-to-day scale, we often imagine it as something that flows. Forward, always forward. One moment leads to the next, and though we may revisit memories or anticipate the future, we move through time in one direction. Never backward, always onward. But physics isn't so straightforward. The equations that describe how particles move, how gravity operates, how quantum fields interact, these are, in many cases, reversible. If you took a video of two particles colliding and played it in reverse, the laws of physics would still hold. The math doesn't care which way time is pointing, and yet, in our experience, time has a clear direction. We wake up older than we were the day before. We remember the past but not the future. A cup of coffee cools over time but never spontaneously warms back up. Dishes fall and shatter. They don't reassemble. Smoke rises, spreads, disappears, never the other way around. This direction, this one-way flow, is often referred to as the arrow of time, and the force behind it, or at least the clearest physical manifestation of it, is something called entropy. Entropy is a measure of disorder, not necessarily chaos, but the number of ways a system can be arranged without changing its overall appearance. The more ways something can be arranged, the higher its entropy. A tidy deck of cards has low entropy. A shuffled deck has high entropy. Both are still decks of cards, but one has more possible configurations. In thermodynamics, entropy explains why heat moves from hot to cold. It's not just about energy moving, it's about probability. There are more ways for molecules to be spread out randomly than there are for them to be neatly arranged in a high-energy cluster. So when a hot object touches a cold one, energy flows not because it has to, but because there are simply more possible outcomes where the energy is spread out than where it remains concentrated. Over time, systems tend toward states of higher entropy. That's not a rule about destruction or decay. It's a statistical observation. The future is more likely to contain disorder than order, because disorder is far more probable. There are more messy configurations than tidy ones. This gradual increase in entropy is what gives time its arrow, not because anything is pushing it forward, but because the direction in which entropy increases happens to align with what we call the future. When we look at the universe as a whole, this becomes even more significant. In its earliest moments, right after the Big Bang, the universe was in a low entropy state. It was hot, dense, and uniform. That might sound like high entropy, everything spread out and energetic, but in terms of gravitational structure, it was extremely ordered. No galaxies, no stars, just an evenly distributed plasma. Over time, small fluctuations grew. Gravity pulled matter into clumps. Those clumps formed stars, then galaxies, then clusters. Structure emerged, complexity increased, and entropy rose. Today, the universe is cooler, less dense, more structured, and much higher in entropy. There are more possible configurations now than there were in the beginning, and that increase isn't slowing down. Black holes, for example, are among the highest entropy objects known. When matter collapses into a black hole, it effectively erases the details of its prior structure. All that information about what it was, how it formed, what it contained, is lost behind the event horizon. What remains is a small number of macroscopic properties: mass, charge, spin, and an enormous amount of entropy. Some physicists even argue that the ultimate fate of the universe, trillions of years from now, will be a state of maximum entropy, a so-called heat death, where all usable energy is gone and no work can be done. Not because energy has vanished, but because it's evenly spread out. No gradients, no movement, no contrast, just uniform emptiness. Whether that's the actual destiny of the cosmos is still uncertain, but it illustrates something important. Entropy isn't just about disorder. It's about what's likely, what's possible, what can happen next, and what can't. It's why we don't see broken things spontaneously reassembling, why we don't wake up younger than we were the night before, why the future is different from the past even if the equations don't insist on it. Because entropy only increases in one direction, and we move with it. Our thoughts, our memories, our biology, all are bound to this drift. A single egg, once scrambled, cannot be unscrambled. Not because it's forbidden by physics, but because the number of ways to be scrambled vastly outweighs the number of ways to be whole. Reversing it would mean arranging every molecule back into its original place, something so improbable that it might as well be impossible. And yet, in every moment, these changes are happening all around us. A candle melts, a battery loses charge, a building decays, not because they're destined to fall apart, but because the journey from order to disorder is overwhelmingly more probable than the reverse. That's the drift, not a force, not a push, just the direction in which things tend to go. And that tendency is what makes time feel real. It's easy to think of time as something that ticks by, something that advances moment by moment, dragging everything along with it. But from a physical perspective, time might not be something that flows. It might be something that simply exists, a dimension, like space, with entropy giving us the illusion of motion. We remember the past because it was lower in entropy than the present. We forget the future because it hasn't yet happened in a high entropy form. Memory, in this sense, is an artifact of entropy, a trail left behind by the system as it moves toward greater disorder. Even our biology reflects this. Cells age, DNA accumulates damage, systems break down, entropy seeps into every level of life. Not because life is doomed, but because life resists entropy only temporarily, through metabolism, through repair, through reproduction. But the drift is always there, in the background, gentle, persistent. This doesn't mean everything gets worse. Entropy doesn't prevent complexity. In fact, it often encourages it. The early universe was simple, uniform, boring. Now it's rich with structure, stars, planets, consciousness. All of it born from tiny fluctuations that, over time, grew under gravity's influence. Complexity is a product of that growth, of systems seeking temporary stability in an unstable environment. Stars form from collapsing clouds, planets form from disks of dust. Life arises, not in spite of entropy, but because of it, taking in energy, using it, releasing waste, always increasing the total entropy, even as temporary order appears. So the arrow of time doesn't just point toward disorder, it points toward change, toward evolution, toward structure that emerges, exists, and eventually fades. That's the rhythm of the universe, not a metronome, not a heartbeat, but a drift, one we cannot reverse. And that drift gives meaning to every process we observe, every cooling ember, every growing tree, every fading memory. All of it points in one direction, not because something is pushing it, but because that's what's likely. And that likelihood shapes how we live. It's why we can plan, why we can predict, why we can look at a snowflake and know it will melt, why we can set a clock and expect it to count forward, not back. Entropy may not be the only reason time feels real, but it's the clearest reason we know. Without it, the past and future would blur. Moments wouldn't stack in order, events wouldn't cascade from causes to effects. And while the rest of physics might still function, our experience of time would unravel. So while entropy is often seen as the enemy of order, it's also the reason we understand sequence. It's the reason stories have beginnings and ends. It's the reason memories feel anchored. And though it never speaks, never commands, never insists, entropy is always there. A gentle drift, a quiet tug, an arrow pointing forward, not with urgency but with certainty. When we talk about motion in space, it's often in terms of visible change, a planet crossing a sky, a comet appearing once every few decades, a spacecraft slowly fading into the distance. These are movements we can imagine, track, and sometimes even watch unfold. But not all motion reveals itself so directly. Some of it speaks more quietly. Across cosmic distances, light becomes the messenger, and its message carries more than just brightness or colour. Embedded in every photon is a trace of where it came from, how long it's been travelling, and how much space has stretched since it began. This subtle shift, this gentle stretching of light over time and distance, is called redshift. It isn't flashy, it isn't something you'd notice just by glancing at a star, but it's one of the clearest signals we have that the universe is not still, that it's changing and expanding and moving us farther from parts of itself with every passing moment. Redshift happens when the wavelength of light becomes longer, when the peaks and troughs of its wave are stretched out, and as the wavelength increases, the light moves toward the red end of the spectrum, hence the name. But redshift isn't caused by just one thing. It can come from motion, from objects moving away from us. That's called Doppler redshift, and it's similar to the way the pitch of a passing siren drops as it moves away. The sound stretches, shifts. With light, the same principle applies, though the scale is different. Then there's gravitational redshift, when light climbs out of a strong gravitational field and loses energy, lengthening its wavelength as it escapes. The difference is often tiny, but detectable with precise instruments. And finally, there's cosmological redshift, the kind that tells us about the expansion of space itself. This is the kind we see most clearly when we look deep into the cosmos. Light travelling through a stretching universe isn't just moving through space, it's being carried by it. And as space stretches, so does the light. This stretching isn't a blur or a distortion, it's a shift, gradual, consistent, and rich with meaning. Because the longer light travels, the more it redshifts, which means that by measuring how much a galaxy's light has shifted, we can estimate how long it's been travelling, and in turn, how far away that galaxy is, or rather, how far it was when the light left. That last distinction is important, because in a universe that's expanding, distance is slippery. The galaxy that sent us its light may now be much farther away than it was when the light began its journey. Space has expanded during the photon's trip. The path it followed has stretched behind it. So when we observe a redshifted galaxy, we're not just seeing something far away, we're seeing something from a long time ago. The redshift becomes a timestamp, not exact to the day, not like a calendar date, but precise in its own way, a measure of how much the universe has changed since the moment that light was born. And in that measurement, we hear a kind of whisper, not a voice, not a language, but a message, carried not in words, but in wavelength. The deeper we look into the cosmos, the stronger that message becomes. Galaxies far away show high redshifts. Their light has been travelling for billions of years, and in that time, the universe has grown colder, larger, and more structured. The light itself hasn't changed. It's still the same energy it always was. But its form has stretched. Its rhythm has slowed. It arrives not in a rush, but in a softened tone. That tone is what astronomers listen for, not with ears, but with detectors and spectrometers and data models. By analysing the light from distant objects, we can extract their redshift. We can map their position not just in space, but in time. And with enough data, we can reconstruct the story of the universe, how it formed, how it changed, and how it's still changing. This is how we know the universe is expanding, not from watching galaxies move, but from hearing what their light is telling us. And the story that light tells is subtle, but consistent. It says, I have come a long way. It says, the space between us has grown. It says, time has passed, and I carry the proof. It's not a dramatic message. There's no countdown, no climax. Just a quiet, continuous shift, photons arriving just slightly redder than they began. That shift is enough. Enough to build models of the cosmos, enough to estimate its age, enough to measure the acceleration of expansion itself. When scientists first began mapping redshifts systematically, they expected a certain pattern, that galaxies farther away would be moving faster, and that the relationship between redshift and distance would be steady. What they found instead was a surprise. The expansion of the universe isn't just continuing, it's speeding up. That discovery, made in the late 1990s, changed our understanding of everything. It suggested that some unknown force, now called dark energy, is pushing the fabric of space apart at an increasing rate. And the evidence for this acceleration came not from direct observation of motion, but from redshift, from comparing how bright and how shifted the light of distant supernovae appeared. Without redshift, this acceleration would be invisible, because galaxies don't carry speedometers, they carry photons, and those photons carry stories. So redshift becomes more than a tool. It becomes a way of listening, not to sound, but to time itself. Each measurement of redshift is a conversation with the past, a data point not just in space, but in sequence, a marker of what was and how long ago it happened. And when you collect enough of those markers, a picture begins to form, not a snapshot, but a film, a record of unfolding, galaxies drifting apart, light stretching, time advancing. The whisper of redshift isn't loud, it doesn't demand attention, but it's persistent, present in every deep space observation, encoded in every spectrum, waiting to be interpreted. Even now, as new telescopes look further than ever before, peering back toward the first stars, the first galaxies, they are guided by redshift, by the subtle change in light that tells them, this is older, this is farther, this is closer to the beginning. It's not flashy work. Measuring redshift is methodical, precise, often slow. But in that slowness there is clarity, and in that clarity, understanding. We don't need the universe to shout. It's enough that it whispers, enough that the light still arrives, that it carries with it the record of distance, of time, of change. Redshift isn't a ticking clock. It's not something you wear on your wrist or hang on a wall, but it marks the passing of time just as surely. Not in seconds or minutes, but in stretches, in shifts, in the deepening red of ancient light. It tells us that the universe is not what it was, that every beam of light is a traveller, and that every traveller arrives changed. Not because the message has been altered, because the space it crossed is not the same as when it left. In that way, redshift is not just a physical phenomenon, it's a witness to expansion, to age, to the distance between what was and what is. It's easy to think of time as a constant, something smooth, regular, indifferent to where you are or what you're doing. A second is a second, a minute is a minute, no matter where you stand. That's how most of us experience it. Uniform, measured, fair. But that's not how the universe experiences it. Out in space, and even here on Earth under the right conditions, time can behave differently. It can stretch. It can slow. Not because the clocks are broken, but because something is bending the structure that time moves through. That something is gravity. Gravity doesn't just pull on matter, it pulls on time itself. This isn't a metaphor. It's one of the more quietly unsettling truths in physics. The stronger the gravitational field, the slower time moves, not just in theory, but in measurable, testable ways. This phenomenon is called gravitational time dilation, and it's a direct consequence of general relativity. Einstein's theory of how gravity isn't a force in the traditional sense, but a curvature of space and time caused by mass and energy. According to general relativity, massive objects warp the fabric of space-time, not just space, but time too. That warping changes how things move, how light travels and how clocks tick. The closer you are to a massive object, the more curved space-time becomes, and the slower time passes compared to regions farther away. It's not just science fiction, it's measurable with precision instruments. The atomic clock on the floor of a building ticks ever so slightly more slowly than one on the roof. GPS satellites orbiting high above Earth must correct for this difference. Their onboard clocks tick faster than clocks on the ground because they are farther from Earth's centre of gravity. If those corrections weren't made, your location data would drift. Slowly at first, then dramatically. Within hours, navigation would be wrong by miles. But the effect becomes even more dramatic near extreme gravitational fields. Near the event horizon of a black hole, the edge beyond which nothing can escape, time slows almost to a standstill, at least from the perspective of an outside observer. To someone falling into the black hole, time would feel normal. Their heart would beat at the usual rhythm, their thoughts would proceed as always. But to someone watching from a distance, those same processes would appear to slow down and eventually stop altogether as the person approached the horizon. They would never see them cross it. The image would freeze, dim, fade. Not because time stopped absolutely, but because gravity's grip had pulled time into a deeper curve, so deep that the signals, the light, the moments could no longer escape fast enough to be seen. This isn't just a theoretical curiosity. It has implications for how we understand the passage of time itself. If time moves at different rates depending on where you are and what gravity surrounds you, then time is not a universal background. It's a local condition, one that can be influenced, altered, slowed. On Earth, the difference is small, but it's there. A clock on a mountaintop ticks faster than one at sea level. Astronauts on the International Space Station, despite moving very fast, actually experience a combination of gravitational and velocity-based time dilation that causes their time to diverge slightly from ours. Over the course of months or years, the difference adds up. Not enough to notice without instruments, but enough that it must be corrected in any system that relies on precise timing. So gravity becomes not just a force, but a timekeeper. Not because it ticks, but because it sets the pace. And the deeper you go into its well, the more it slows the hours. Think of time as a river. In flat space, far from massive objects, the river flows smoothly, quickly. But near a planet or a star or a black hole, the river slows. It deepens, the current drags, and if you float down into it, time drags with you. Not metaphorically, literally. The seconds pass more slowly. The rate of change decelerates, and yet, from your perspective, everything still feels normal. Because your body, your mind, your biology, all of it is moving through the same bent river. Only someone outside the well in flatter space would see the difference. This leads to strange consequences. You could, in principle, spend time near a massive object where gravity is intense, then return to a region with weaker gravity, and find that more time has passed for others than for you. Not just as an idea, but as a measurable fact. Time, once thought to be universal, becomes personal, shaped not by intention or preference, but by the invisible hand of curvature. This curvature isn't something you feel. Gravity feels like a pull downward, an attraction toward mass. But the warping of space-time happens in dimensions we don't directly sense. It takes instruments, equations, and observations to reveal it. And yet, the consequences are everywhere. Satellites would drift without corrections. Physics experiments would misfire. Long-distance communications would fall out of sync. Even though gravity's grip on time is subtle at Earth's surface, our machines are precise enough to notice, and they must notice, or they will fail. In this way, gravity quietly sculpts time, not in bursts, but in gradients, not with rhythm, but with resistance. It slows time not in stops and starts, but in curves and slopes, like a hill so gradual you don't realize you're climbing it. The concept becomes even stranger when applied to the cosmos as a whole. In regions of deep gravity, near neutron stars, near black holes, even within the cores of massive galaxies, Time runs differently than it does in the vast voids between. These differences are small across galactic scales, but real, and over the age of the universe they add up, which means that in different places different amounts of time have passed, that the age of the universe, as measured locally, might not be exactly the same everywhere, that gravity has not only shaped where things are, but when they are. It's a quiet idea, but profound. Because it means time is not just something that happens everywhere equally. It's something that is shaped gently but persistently by the presence of matter. A planet, a star, a galaxy. Each creates a well in space-time, not just in shape, but in tempo. And those tempos define the local experience of time. This isn't something we notice in daily life. The differences are too small, but they're there, underneath everything. Gravity's grip isn't just physical, it's temporal, and it's steady, always pulling, always slowing, always defining the pace of the moments that pass nearby. So if you've ever wondered why time feels different in different places, slower in the quiet of the mountains, faster in the noise of the city, part of that is perception, but part of it is physics. Time really does move differently. Not much, but enough. Enough to notice, if you know where to look. Enough to measure, if your instruments are tuned. Enough to remind us that time, like everything else in the universe, is part of a structure that bends, curves and shifts under the influence of mass. And that bend is not just a shape, it's a delay, a stretch, a slowing of the hours, not because they're resisting, but because they're following the shape of the world. There's a strange kind of silence in the universe, not the absence of sound, but the presence of something that doesn't speak in light, something that doesn't glow, doesn't reflect, doesn't scatter photons in any way we can easily detect. And yet, it's there. Measurable not through sight, but through influence. This is dark matter. Not dark because it's hidden behind something, or because it absorbs light like a shadow, but because it doesn't interact with light at all. It's transparent, invisible, silent, except for the way it bends space. And in bending space it bends time, not in abrupt ways, not like a black hole or a neutron star, but in subtle curves, gentle warps, shifts in gravity that ripple outward from mass we cannot see. Dark matter doesn't emit radiation, it doesn't spark or shine. We wouldn't know it was there at all if not for the way galaxies move. When astronomers began studying spiral galaxies in detail, they noticed something odd. The stars at the edges weren't behaving the way they were supposed to. Based on visible mass, all the stars, gas and dust, the outer stars should have been moving slower than those near the centre. Gravity weakens with distance. The farther out you go, the less mass there should be pulling you in. The rotational speed should taper off, but they didn't. The stars at the edges of galaxies were moving just as fast as those near the core, not slightly off, wildly off. That discrepancy didn't go away with better data. It became clearer, stronger, more consistent across thousands of galaxies. The only way to explain this motion was to assume that there was more mass than we could see, something invisible providing the extra gravity needed to hold those fast-moving stars in orbit. That something was called dark matter. It's not one particle, not one theory, it's a placeholder term for whatever accounts for this unseen mass. And the more we've studied it, the more essential it's become. Dark matter appears to make up about 85% of the total matter in the universe, not a side effect, not a fringe addition, the main ingredient. It surrounds galaxies in vast halos, extending far beyond the visible edges. It fills the space between clusters. It holds structures together that would otherwise fly apart. And because gravity shapes time, this invisible mass influences not just how galaxies rotate, but how time passes in their vicinity. Not in a way you'd feel, but in a way that changes the curvature of space-time. The distribution of dark matter determines where gravity wells form. Those wells, in turn, affect how fast time moves in their depths. Wherever dark matter is dense, time slows, slightly, imperceptibly but measurably. And because dark matter is everywhere, these subtle influences are everywhere too. They shape the flow of time across the universe, not directly, but structurally. Time curves where space curves, and space curves where mass is, and most mass is dark. This means that even though we cannot see dark matter, we move through the geometry it creates. We live inside its contours. Our galaxies orbit within its arms. Our light travels through its unseen presence. Our time bends inside its grip. It's not something we can avoid. It's not something we can isolate. It's the scaffolding on which the universe is built. You could think of it like walking through wind you can't feel, only realizing it's there by the way the leaves move around you. The air doesn't speak, but the trees do. In the same way, dark matter doesn't glow, but the stars it holds in place tell its story. And that story has shaped the timeline of the cosmos. Without dark matter, galaxies wouldn't have formed as they did. The clumps of matter that seeded them would have dissipated too quickly. There wouldn't have been enough gravity to gather the gas, to trigger star formation, to build the structures we now see. The early universe, full of light and energy, was also full of dark matter, pulling, clustering, guiding. It didn't block the light. It didn't compete with it. It shaped the paths it followed, and because of that, it shaped time itself. Not just where time flows faster or slower, but how it unfolds. The web of galaxies that stretches across the cosmos, that vast structure of filaments and voids, reflects the distribution of dark matter, and in turn the distribution of time dilation, curvature, and evolution. When we simulate the universe, trying to recreate its shape from first principles, we need dark matter to make it work. Without it, nothing looks right. The timelines don't match, the clustering is off, the flow of structure through time doesn't line up with what we observe. But when we add it, invisible though it is, everything begins to click. Timelines align, galaxies form, expansion unfolds. Dark matter doesn't just balance the math, it sets the rhythm, not by ticking or turning or pulsing, but by creating the gravitational wells through which time flows. And while that rhythm is not audible, not touchable, it's consistent, it's foundational. There's something quieting in that idea, that so much of time's flow is shaped not by what we see, but by what we don't, that the invisible can define the visible, that the unmeasurable can become measurable through influence, and that mass, even silent, can leave a signature on every passing hour. There are other theories, of course. Some physicists wonder if what we call dark matter is really a gap in our understanding of gravity, that maybe the rules change at large scales, and we're mistaking a new form of physics for an unknown substance. But so far the evidence leans toward the presence of something real, not imagined, not invented, real but hidden. And in that hidden presence, time continues to unfold. The stars orbit, the galaxies spin, the light bends, the moments pass, faster in the voids, slower near the clusters, shaped by contours that can only be traced by inference. This influence isn't flashy. It doesn't cry out for attention, but it's constant. The stars trust it, the galaxies depend on it, and we, unknowingly, are shaped by it. The time we experience, the pace at which our galaxy turns, the curvature of our local space, the slight drifts and distortions in the starlight we observe, all of it is tinted by something we cannot detect directly. Dark matter doesn't keep time in the way a clock does. It keeps time the way a valley holds a river, by setting the path, by shaping the flow, by providing the structure through which time can move, not quickly, not slowly, but inevitably. And even as we continue to search for the particles, the fields, the answers, its presence continues to guide the universe, without sound, without light, but never without consequence. The stars are drifting, slowly, Steadily, the galaxies are pulling away from one another. The space between them isn't just expanding, it's accelerating. The distance isn't growing linearly, like the widening ripples of a pond. It's speeding up, stretching faster and faster with every moment that passes. This was not always expected. For much of the 20th century, it was believed that the universe's expansion, the stretching set into motion after the Big Bang, was gradually slowing down. Not stopping necessarily, but coasting. Gravity, it was thought, would eventually apply the brakes. Maybe it would bring the expansion to a crawl. Maybe, in some scenarios, it would reverse it entirely. A cosmic contraction. A big crunch. That's not what happened. In the late 1990s, two teams of astronomers set out to measure how fast the universe was slowing down. They looked at Type Ia supernovae, bright, distant explosions that occur in predictable ways. These supernovae serve as standard candles, meaning their intrinsic brightness is known. By comparing their true brightness to how dim they appear from Earth, scientists can estimate their distance. But the distances didn't line up with expectations. The supernovae were dimmer than they should have been, not because they were less powerful, but because they were farther away than the existing models predicted. The only conclusion was that the expansion of the universe wasn't slowing down at all, it was speeding up, and the force behind that acceleration was given a name: dark energy. The term is simple, but misleading. It's not dark in the way dark matter is, as in unseen mass-exerting gravitational pull. Dark energy doesn't clump, it doesn't attract. It does the opposite, it pushes, it drives space apart. And it's not energy in any conventional sense. We don't know what it is. Not really. It's a placeholder, a label for the observed fact that the expansion of space is accelerating. That space isn't just expanding into emptiness. The expansion itself is being pushed by something we can't identify. Estimates suggest that dark energy accounts for nearly 70% of the total energy content of the universe. Not a footnote, not a minor contributor, the dominant component, but it reveals itself only through expansion. We don't detect it in a lab. We don't measure it in collisions. We observe its influence in the way galaxies drift apart more quickly than they used to, in the way distant light stretches more than expected, in the unfolding beat of space itself, a rhythm growing faster with time. This unfolding isn't chaotic. It isn't violent. It's slow, quiet, but persistent. The further something is from us, the faster it appears to recede. Not because it's moving quickly through space, but because the space between is expanding more rapidly. And as that space grows, it accelerates again. This is how dark energy works. It doesn't speed things up in a burst. It changes the tempo of space, a tempo that governs the distance between galaxies, that stretches the light from ancient stars, that defines the horizon of what we can see. The effect is only noticeable over vast scales. Within a galaxy, gravity is strong enough to hold matter together. The stars in the Milky Way aren't being torn apart by dark energy. The planets in the solar system are not drifting from the sun. Those systems are bound. They resist the push. But between galaxies, in the wide dark gaps where gravity is weak, the expansion wins, and the expansion is accelerating. That means our view of the universe is slowly narrowing, not in angle, but in access. Galaxies that are distant today will become unreachable in the future. Their light, even moving at the fastest speed nature allows, will be stretched so far that it never reaches us. Already there are galaxies beyond our observational horizon, places from which no new information can arrive. Their light is trapped in the ever-stretching space between. In time, more and more of the universe will slip away, not disappear, just drift so far and so fast that we will no longer be able to detect it. This is not a disaster. It's not a rupture or a tearing. It's the unfolding beat of a universe under the influence of dark energy. It is a slow fade, a cosmic hush, a growing stillness. That stillness is only partial for now. Our local group of galaxies, including the Milky Way and its neighbours, is gravitationally bound. It will remain together. Eventually galaxies may merge, stars may fade, but they will not be pulled apart by expansion. It's everything else that will drift, and the future will be quieter for it. From a timekeeping perspective, dark energy complicates things. It changes the trajectory of cosmic evolution. It alters the relationship between redshift and distance. It affects how we estimate the age of the universe because expansion isn't just continuing, it's quickening. Time, shaped by expansion, becomes a function of this unfolding. The more expansion accelerates, the faster the observable past recedes. The tempo of change becomes curved, like a song slowly increasing in speed without end. But it's not something we feel. It's not something that speeds up our days or shortens our breaths, because our lives are confined to a pocket of space where dark energy's influence is negligible. It is only across billions of light years that the beat changes. There are different theories about what dark energy might be. Some believe it is the cosmological constant, a term Einstein introduced into his equations, then famously called his greatest mistake. It represents a constant energy density filling space itself, unchanging over time. Others suggest it might be a field, something dynamic, evolving, shifting across the universe. There are even possibilities that what we call dark energy is the result of something deeper, a modification to gravity on large scales, or a byproduct of quantum fluctuations in empty space. None of these ideas are confirmed, but all of them attempt to explain the same thing: why space stretches faster with time, and whatever the explanation, the effect is unmistakable. We live in a universe where the beat is changing. Not drastically, but enough. The unfolding isn't uniform, it's increasing, and that increase defines not just the shape of space, but the reach of time, because time in cosmology is often measured through observation, how far we can see, how much light has travelled, how old the structures are. But in a universe ruled by dark energy, that visibility has a ceiling. There are limits, and as expansion continues to accelerate, those limits grow closer, not because time is ending, but because time is stretching. The path to the past gets longer, the light takes more time to arrive, and eventually there are places we simply cannot know. This doesn't mean the universe is becoming smaller. It means the part we can touch, the part we can measure, is becoming more isolated. Like islands in a sea that grows wider with each wave, that sea is silent, unobstructed, and guided by something we do not yet understand. Still, we can observe it, map it, chart its influence. And in doing so, we find that the tempo of the cosmos is not steady. It is shifting, not as a pulse, not as a clock, but as a gentle, accelerating beat, one that unfolds with every passing moment, reshaping the structure of what's possible to see, to know, to remember. For most of human history, time was imagined as something absolute, an invisible current flowing everywhere at the same rate, independent of anything else. It was a convenient idea. It made time feel solid, predictable, something you could lean on. But in the early 20th century, that idea began to unravel. The first crack came from Einstein's theory of special relativity, published in 1905. It began with a simple question: what happens when two observers are moving relative to each other? The answer, surprisingly, was that they do not agree on time. Their clocks tick differently. Events that appear simultaneous in one frame do not appear simultaneous in another. Time, it turned out, was not absolute. It was relative. That alone would have been enough to change physics forever. But the implications went deeper. If time could stretch or compress depending on how fast you're moving, then it's not a background constant. It's a variable, one that depends on your perspective, your speed, your path through space. According to special relativity, the faster you move, the slower time passes for you, relative to someone standing still. This isn't a trick of perception. It's a physical effect, backed by experiment. High-speed particles decay more slowly than their low-speed counterparts. Astronauts moving at high velocities age ever so slightly more slowly than people on Earth. The faster you go, the more time dilates. And at the speed of light, time, from the perspective of a photon, essentially stops. That's a strange thought. From the photon's point of view, there is no time between emission and absorption. It's created and destroyed in the same instant, even if billions of years pass for everything around it. That's what relativity does. It shatters the idea of a universal now. There is no single moment that exists for everyone, everywhere. Now is not a flat slice through the universe. It's tilted, warped, variable. What you consider the present depends on where you are and how you're moving. And then came general relativity. In 1915, Einstein extended his ideas to include gravity, not as a force, but as a curvature of space-time itself. Mass and energy bend the fabric of space-time, and objects move along the curves created by that bending. It wasn't just space that curved, time did too. And in curved space-time, clocks tick differently depending on where they are. In a gravitational well, time moves more slowly than it does farther away. We've measured this. Place two precise clocks at different altitudes, one near sea level, the other on a mountaintop, and you'll find that the one at higher elevation ticks slightly faster. Not by much, but enough to measure. Enough that the difference must be corrected for in satellite systems like GPS. This bending of time isn't an illusion, it's part of the structure of reality. In relativity, space and time are not separate entities. They're woven into a single fabric, space-time, and movement through one affects the other. This leads to something even more counterintuitive. Every object moves through space-time at the speed of light. That sounds strange, but consider this. An object at rest in space is still moving through time. An object moving through space begins to move more slowly through time, in order to keep the total space-time speed constant. It's like sharing a budget. The more you spend on space, the less you have left for time. This interdependence means that time isn't just influenced by movement and gravity. It is inseparable from them. You can't move through space without affecting your motion through time. You can't enter a gravitational field without changing your experience of duration. And because mass bends space-time, the path of light itself curves, not because light is attracted to mass, but because the space it travels through is curved. The path is straight, but the geometry isn't. This curvature of space and time leads to all kinds of phenomena. The bending of starlight around the sun, observed during an eclipse, the slow precession of planetary orbits, the stretching of time near massive objects, all of it confirmed, observed, measured, and all of it pointing to a single truth. Time, like space, is flexible. It can bend, it can stretch, it can slow, but it cannot remain untouched. There is no location in the universe where time flows identically to all others. There is no clock that runs truly universally. This doesn't mean time is chaotic or random. It follows precise rules. But those rules are more complex than once imagined. They involve geometry, mass, velocity, curvature. Relativity doesn't eliminate time. It contextualizes it. It tells us that what we experience is local, that every clock, every heartbeat, every second counted. All of it happens within a patch of curved space-time, shaped by everything around it. The practical effects of this are subtle in everyday life, but immense in understanding the universe. When we look at distant galaxies, we're not just seeing light delayed by distance, we're seeing light affected by curved space-time, light that has passed near massive structures, been stretched by expansion, slowed by gravitational wells. Every observation is shaped by relativity. Every measurement of time, every calculation of age or distance must include it. And as we explore deeper into the cosmos, this becomes more than a correction. It becomes a foundation. Without relativity, our models of the universe don't work. With it, they become precise, predictive, coherent. There's a kind of humility in this realization. That time, which feels so personal, so internal, is actually part of a vast, flexible structure. That our hours, our minutes, our memories, all happen along curves we cannot feel. That the ticking of a clock is not absolute, but relative to motion and mass. And that when we try to build a picture of the cosmos, we must first understand how time bends beneath our feet. This doesn't make time less real. It makes it more intricate, more connected, more dependent on context. When time loses its footing, when it no longer stands apart as a constant, it becomes something richer, a dimension, a path, a variable written into the fabric of the universe. And as we move through that fabric, we move through time, not on a rail, not on a schedule, but on a curve shaped by everything around us, everything we see and everything we don't. If you were to look closely enough at the world around you, not with your eyes, but with instruments capable of seeing past molecules and atoms, beyond electrons and nuclei, you would find that the surface of reality begins to break apart. Not into smaller pieces exactly, but into probabilities, into behaviours that refuse to settle into single outcomes until observed. This is the realm of quantum mechanics, and time, here, behaves differently. At macroscopic scales, the scale of watches and calendars and orbits and aging, time moves forward in a way that seems inevitable. Events unfold in sequence. One thing follows another. You know what came before. You can't predict what comes next with certainty, but you assume that something will come. The past is fixed, the future uncertain. But in quantum physics, the distinction isn't always so clear. Particles don't follow strict paths. They exist in superpositions, combinations of possibilities. Until measured, an electron might be here and there at once. A photon might travel every path, not just one. The world exists not as a single timeline, but as a range of potential timelines, all coexisting until something, an interaction, an observation, collapses the possibilities into one. And time in this framework isn't always part of the equation. That's one of the stranger facts about quantum mechanics. The fundamental equations that describe how quantum states evolve, like the Schrödinger equation, do include time, but they do so in a way that's more like a backdrop than a participant. Time is treated as a parameter, not a variable that itself has dynamics. It doesn't flow or bend or respond to the system, it's just there, a marker for change, a placeholder. But if time is only a parameter, not a dynamic quantity, then what does that say about its reality? And what happens when we try to unite quantum mechanics with general relativity, a theory where time is anything but fixed? The two theories don't fit neatly together. One treats time as an external, unchanging label. The other treats it as part of a malleable geometry, shaped by mass and energy. This mismatch has made the search for a theory of quantum gravity, a theory that unites the quantum and the cosmic, incredibly difficult. In some formulations of quantum gravity, time disappears altogether. In the Wheeler-DeWitt equation, for example, a central equation in attempts to describe the quantum state of the entire universe, there is no time variable at all. The universe, in this view, simply is. Every possible configuration of space and matter is encoded in a single timeless object. Change doesn't happen in time. Time emerges from change. That's not easy to imagine. A universe without time. A cosmos where everything that ever happens, every fluctuation, every movement, every sequence, is encoded in a single static structure. No ticking, no progression. Just a kind of eternal now, from which the illusion of flow emerges. In this view, time is not a fundamental property of the universe. It's an emergent one. Something that arises only when the system is large enough, or when a certain kind of interaction takes place. You could think of it like temperature. At the level of a single particle, temperature doesn't make sense. It's not a property you can assign to one molecule, but when you have a collection of them, billions, trillions, temperature emerges. It becomes meaningful, measurable. Maybe time is like that. Not real at the level of the fundamental equations, but real in the way experience is real, arising only when enough interactions occur, or when observers are present, or when systems are large enough to contain clocks. But if time is emergent, then what exactly is a clock? In quantum physics, a clock can be any system that changes in a predictable way. A decaying particle, a spinning electron, an oscillating field. But in a closed quantum system, one not interacting with anything else, time becomes ambiguous. Without an external observer or a reference frame, there is no clear distinction between before and after. The system evolves, yes, but evolution doesn't imply a flow of time unless there's something to compare it to. This leads to one of the deeper puzzles in physics, the problem of time. How do you define time in a universe where everything, including the observer, is part of the quantum system? If you can't step outside the universe to check the clock, then how do you know what time it is? Some proposals try to solve this by identifying an internal clock, a subsystem within the universe that can serve as a reference for everything else. If you can find a part of the system that evolves in a consistent way, you can measure time relative to it. But even this is provisional, because in the end it's all relative. You're not measuring time absolutely, you're measuring change with respect to change, a clock without hands, just shifting states. This is where quantum mechanics and human experience part ways. We feel time, we remember, we anticipate. But at the quantum level, those concepts dissolve. The wave function doesn't record memories. It doesn't store direction. It simply evolves according to its rules, without any sense of past or future. Some physicists argue that the arrow of time, the direction we experience, is tied not to the quantum laws themselves, but to the way quantum systems decohere. Decoherence is what happens when a quantum system interacts with its environment, when its delicate superpositions break down and it behaves more classically. It's not that the system changes its rules, it's that the act of interaction causes information to leak, and in that leakage the arrow of time is born. Because information flows one way, once lost, it can't be retrieved in the same form. Just like entropy increases in thermodynamics, decoherence increases in quantum systems, and that increase defines direction. Not because the universe commands it, but because it's more probable, more likely, more consistent with observation. This connects time, not just to geometry or motion, but to information. The more you know about a system, the more precisely you define its state, the more you constrain its future. But as information degrades, as systems decohere, uncertainty grows, options multiply, time unfolds. This is time not as a ticking clock, but as the unfolding of possible states, a bloom of outcomes, a cloud narrowing to a point then blooming again, and somewhere in that narrowing, that moment of measurement or experience, a timeline takes shape. Not because time flowed into it, but because that's how the system settled. There is beauty in that. A universe that doesn't rely on an external stopwatch. A cosmos that builds its own clock out of interactions, out of relationships, out of change. That clock has no hands, no dial, no face, but it ticks in its own way. Every quantum event, every transition, every moment of entanglement, all of it contributes to the rhythm, not a rhythm we can hear, but one we can observe, measure, map. And even if time is not fundamental, even if it emerges from something deeper, it still shapes how we live, how we perceive, how we remember. Quantum mechanics may not offer a comforting picture of time. It may dissolve our intuitive sense of sequence. But in that dissolution, it offers something else. A reminder that time is not simple, not singular, not settled. It is layered, conditional, built from interactions we don't see, happening in realms we barely understand. But the effects are real. They reach us, shape us, and though the clock has no hands, we're still inside it, watching it unfold, one uncertain moment at a time. There's a scale at which our usual tools break down, not the physical tools, not telescopes or particle accelerators, but the conceptual ones, the frameworks we use to understand space, time, and cause. Push far enough in either direction, big or small, and those frameworks start to strain. Then they crack, and nowhere do they break more abruptly than at the beginning. Not the beginning of a story, or a process, or a structure, but the beginning of time itself. Right now we measure time with increasing precision. Atomic clocks tick billions of times per second. Some instruments can measure variations so small they'd lose only a second over the entire lifetime of the universe, and yet those instruments are still vastly too slow to glimpse the smallest meaningful unit of time. That unit is called Planck time. It's not a measurement you can observe directly, or a moment that ever appears on its own. It's a boundary, a threshold beyond which our equations stop giving meaningful answers. Planck time is the smallest interval of time with any physical meaning, based on the fundamental constants of nature. Roughly, it is 539 sus 10 or 44 seconds. That's not just short, it's unimaginably short. You could fit more Planck intervals into a single second than there are grains of sand on Earth, or stars in the observable universe, by an amount that itself defies analogy. This scale doesn't come from technology, it comes from theory. Specifically from the combination of three constants: the speed of light, Planck's constant, and the gravitational constant. When you put those together in a way that gives you units of time, the result is Planck time. It's not just arbitrary, it's fundamental. Planck time represents a kind of limit, not necessarily the smallest time that can ever exist, but the smallest time where our current understanding still applies. Below that scale, we have no working theory. Space and time might not even be smooth anymore. They might not exist at all in the way we think of them. To reach Planck time, you have to go back, way back, to the first moment after the Big Bang. Not the first second, not even the first nanosecond, but the first fraction of a fraction of a fraction of a second. The earliest possible instant that can be meaningfully described by physics as we know it. Before that, we can write down ideas, but we can't test them. We don't know what time means when time hasn't had time to emerge. The universe at that scale was smaller than a proton, denser than any black hole, hotter than any star, and more importantly, it may not have had time in any familiar sense. If time requires structure, if it requires change or interaction or a reference frame, then the very beginning may not have had any of that. It may have been a kind of timeless state, or a quantum superposition of possible beginnings, or something else entirely. But at Planck time, something shifted. The universe, for reasons we still don't fully grasp, began to expand. Rapidly. Not just space, but space-time. Not from a centre, but from everywhere. And with that expansion, the foundations for time were laid. Not clocks, not rhythms, but the capacity for cause and effect. The conditions for interactions, the emergence of structure, the unfolding of a timeline. From that first tick, everything else followed. Quarks formed, then protons and neutrons, then atoms, then stars. But it began at a scale we still don't know how to describe. The Planck epoch, the first Planck second of the universe, is a blind spot in our understanding. We can calculate what came after. We can see the fingerprints of inflation, of cooling, of structure. But the tick itself, that first measurable instant, remains out of reach. Not because it's too small to observe, but because the nature of time itself may not be smooth at that scale. Some physicists suspect that space-time is quantized, that it's made of discrete units, like the pixels on a screen. Not because it looks that way, but because treating it as continuous leads to infinities that break our equations. If space-time is granular, then Planck time might be the shortest possible frame. the universe might move not like a film with infinite frames per second, but like one with a hard resolution, a minimum tick, not in a choppy or broken way, but in a way that's hidden beneath the scales we can currently probe. Other theories suggest that at the Planck scale, space and time give way to something else entirely, a quantum foam, a turbulent sea of temporary geometries, where up and down and before and after cease to have their usual meanings. If that's true, then time, at its root, is not even a line. It's a probabilistic fabric, one that's smoothed out into sequence only when viewed from a distance, like a pointillist painting that reveals its image only from across the room. This has profound implications for everything that follows, because if the first tick of time wasn't really a tick, if it was instead a kind of statistical emergence from a deeper chaos, then everything we experience as time is the result of an averaging process. The flow we sense might be real, but it might also be the result of underlying randomness, filtered through large-scale order. That doesn't make time less real. It makes it more mysterious. Because the closer we get to the beginning, the more time itself becomes slippery. Even the concept of before the Big Bang loses meaning. If time began at Planck time, if causality only becomes possible at or after that scale, then the word before might be incoherent. There may not be a before, there may only be conditions that do not yet include time. From our current understanding, time and space emerge together. They are aspects of the same unfolding, and that unfolding began, as far as we can trace it, at the Planck scale. From that point onward, time as we know it becomes increasingly familiar, not immediate but understandable. Thermodynamics takes hold, entropy begins to increase, events follow one another, but the transition from timeless to timed is still opaque, and Planck time is the boundary between the two. This makes it more than a number. It makes it a horizon, not in space but in understanding. A reminder that even our most basic assumptions, that time flows, that events proceed, that cause follows effect, may only apply within certain domains, and that beyond those domains the universe may not be obligated to make sense, at least not in the ways we expect. Still, Planck time gives us a starting point, a place to begin measuring, a place to begin asking questions. What mechanisms could have triggered inflation? What quantum properties defined the earlier state? How did causality arise from symmetry? And what does it mean to measure time when there are no clocks yet? These questions aren't just philosophical, they are deeply physical. They are tied to the core of what we call the observable universe, and though we cannot yet answer them, we can point to where the answers must begin. Not at the beginning of time, but at the beginning of meaning, and that beginning lies just beyond the smallest tick we've ever named. Black holes are often described as destroyers. They consume, collapse, swallow. They pull in matter, trap light, bend the fabric of space until the geometry itself breaks down. And yet, for all their violence, they are also among the most precise objects in the universe, defined entirely by just a few properties: mass, spin, and charge. They have no surface, no structure, no internal weather. They're simple and absolute. But if you ask whether they keep time, the answer becomes far less simple, because time near a black hole doesn't behave the way it does elsewhere. Outside a black hole, time still has a rhythm. Seconds pass, clocks tick, processes unfold. But the closer you move toward the event horizon, the boundary beyond which nothing escapes, the more that rhythm begins to stretch, slow, distort. From far away, an object falling toward the horizon appears to freeze. Its motion slows to a crawl. Its light redshifts into invisibility. It never quite reaches the edge. Not because it stops moving, but because time, from an outside perspective, stops moving for it. To an observer falling in, time feels unchanged. The seconds pass normally. The pull increases, the curvature tightens, but the experience of time stays coherent. It isn't until the singularity, the point of infinite density at the black hole's centre, that the laws of physics themselves begin to fail. But from the outside, the story is different. To you, watching from a safe distance, time near the event horizon bends so severely that it never quite passes. The falling object lingers, fades, stalls just above the boundary, not physically, but in terms of its last visible light, stretched thin across time. In that sense, black holes appear to freeze time. They don't stop it exactly, but they slow it beyond usefulness. They drag it into a curve so deep that the clock all but stalls. This makes them natural laboratories for time dilation. No other environment in the universe bends time so sharply in such a localized region. Even neutron stars, those dense, collapsed cores of massive stars, can't match the gradient of time found near a black hole. But the question isn't just whether time slows near a black hole, it's whether time once inside exists at all. And that question is harder to answer. Because what happens beyond the event horizon isn't just hidden from view, it's causally disconnected from the rest of the universe. Events inside cannot send signals out, information doesn't return. From our point of view, what happens inside a black hole is unknowable, not just difficult to observe, fundamentally beyond reach. But that doesn't stop physicists from asking the question. Does time proceed normally for an infalling observer? Does the singularity represent an end to time? Or is the very notion of time, once inside, meaningless? Some models suggest that time continues to flow until the singularity is reached, a point where space-time curvature becomes infinite. But those models rely on classical general relativity. They don't include quantum effects, and at such extreme scales, quantum effects become unavoidable. Others argue that black holes might not contain singularities at all, that some form of quantum gravity prevents the formation of infinite densities, and that time may continue in a different form beyond what we currently understand. Loop quantum gravity, for example, posits that space and time are quantized, made of discrete units. In this view, the interior of a black hole might bounce, converting collapse into expansion, or channeling the contents into a new region of space-time entirely. In such scenarios, time doesn't end, it transforms. But in the classical picture, the singularity is final. It's not just a place where matter goes, it's where the geometry of time itself breaks down. There is no future past the singularity, and without a future, what does it mean to have time at all? Even the event horizon, often treated as a boundary in space, is more accurately a boundary in time. Cross it, and all possible paths lead inward. Not because there's a wall, but because the structure of space-time has rotated. The direction we think of as time now points toward the singularity. Inside the event horizon, time and space trade roles. To an infalling object, the singularity lies in the future, not in space. It's not something you can avoid by turning or steering. It's something that lies ahead of you, like tomorrow. And just as you can't choose to move into yesterday, you can't choose to steer away from the singularity. This reframing makes the black hole not just a gravitational object, but a temporal one, a place where the geometry of time is fundamentally altered, where the future becomes singular, where options collapse into certainty. That collapse is more than just a consequence of gravity. It's a restructuring of possibility, and it raises difficult questions. If black holes swallow information, as they appear to, then does that information remain frozen inside? Or does it evaporate, vanish, erode? Stephen Hawking famously showed that black holes emit radiation, not from inside the event horizon, but from quantum fluctuations near it. This radiation, now called Hawking radiation, carries away energy. It causes the black hole to shrink, very slowly at first. But over immense timescales, this evaporation could lead to the disappearance of the black hole entirely. But if the black hole vanishes, what happens to the information that fell in? In quantum mechanics, information can't be destroyed. The evolution of a quantum system is unitary, meaning the present must encode the past. But if a black hole evaporates completely, and that information is gone, then the unitarity of quantum mechanics breaks. This is the information paradox. It pits general relativity against quantum theory. Each foundational, each precise, but incompatible in this one crucial respect. And time, as always, is at the centre of the puzzle. Because information is about sequence, memory, order. It defines how the past becomes the present. If that chain is broken, if the connection is lost, then time itself becomes unanchored. Solutions to the paradox vary. Some argue that information is somehow encoded in the Hawking radiation, that subtle correlations preserve the past even as the black hole fades. Others suggest that black holes have no interior in the conventional sense, that everything happens at the horizon in a kind of holographic encoding, where the surface holds the full description of the volume. Still others propose that information isn't lost, but becomes inaccessible in a way that mimics loss, a kind of practical but not fundamental erasure. Whatever the answer, the question remains the same. Do black holes destroy time, or do they simply reshape it in ways we don't yet understand? So far, we don't know. We can't peer inside. We can't test what happens at the singularity. But we can model the approach. We can measure the warping, and we can observe the slowing, that strange, infinite pause that happens just before the edge is crossed. In that pause, we see time's limits, not because the laws fail, but because they are pushed to their extreme. A clock falling into a black hole won't stop ticking from its own point of view. But from ours, it will tick more and more slowly until its final second stretches into eternity. And then it fades, not just from sight, but from the timeline itself, not because it ceases to exist, but because it exits our causal world. What lies beyond is not just space we cannot reach, it's time we cannot share. In the world of physics, time is usually treated as a dimension, one that can be measured, warped, and experienced depending on your frame of reference. But increasingly, time is also showing up in places we don't usually associate with dimensions at all. Not in the natural world, but in the artificial one. Simulations, models, virtual environments. These are not abstract philosophies or science fiction stories. They are systems we build and use every day, not to replace reality, but to reflect it, predict it, interact with it on scales and in ways that are otherwise inaccessible. And in these systems, time behaves differently. It has to. A simulation, by definition, is an approximation. Whether it's modelling the climate, tracking particle collisions, or rendering a digital landscape in a video game, it runs on a machine. It runs on code. And that code includes some version of time. But simulated time is not continuous. It does not flow. It steps. One frame, then the next, tick by tick, determined by the speed of a processor and the structure of a program. In this space, time is a sequence of updates, not dictated by the laws of physics, but by the rules we write. It might resemble physical time, it might even mimic relativistic effects if the code is written that way. But fundamentally it's synthetic, a scaffold for interaction, a timeline built to organize computation. And yet, when we run a simulation, say of two galaxies colliding, we still speak of seconds and years. We track the system using familiar units. We interpret it as if time were flowing inside. But it isn't. Not really. The particles don't know what a second is. The variables don't care about duration. They exist only as values in memory, changing from one state to the next. If a simulation pauses, time stops. Not within the simulation, but within the structure we've built to represent time. When it resumes, time continues. But that continuity is a choice, not a property. This introduces an idea that feels subtle at first, but grows more profound the longer you think about it. Time inside a simulation is not time at all, unless you treat it that way. It's structure, it's bookkeeping, It's order applied to processes, and that makes it both artificial and astonishingly familiar. Because if time in a simulation can be written, paused, reversed, or even deleted, then the experience of time for anything inside that simulation is entirely dependent on the rules assigned to it. And that raises a question. If the universe we inhabit were a simulation, not metaphorically but literally, how would we know? Would time, as we experience it, be any different? Would clocks still tick? Would the past still feel like memory and the future like uncertainty? Or would our experience of time be indistinguishable from the one we have now, even if, under the surface, every moment was just a sequence of state changes in some deeper system? This is not a question of belief. It's a testable, if currently unprovable, proposition in theoretical physics. The so-called simulation hypothesis suggests that if it's possible to simulate conscious beings with realistic experiences, and if those simulations vastly outnumber real experiences, then statistically it's more likely we're inside one. That hypothesis is not universally accepted, nor does it rest on solid scientific footing, but it invites us to reconsider how we define time, because if simulated time can feel real from the inside, if it can be built to function indistinguishably from natural time, then perhaps time itself is less about its underlying substrate and more about structure and sequence. In simulations, we often create virtual clocks. These are not ticking objects, they are counters, variables that update at regular intervals. But to a process inside the simulation, a digital organism, a virtual agent, those counters can serve the same role as a wristwatch does for us. They define when to act, when to wait, when to move. They create rhythm. And that rhythm defines the difference between now and later, between memory and anticipation. Even in artificial intelligence systems, trained in environments where time is simulated, the behavior of agents is often deeply dependent on timing, reaction times, learning rates, delay periods. Time, even in a virtual world, shapes behavior, but the simulation doesn't know it's keeping time. It's just running instructions in order. That order, though, is everything. Without it, nothing makes sense. Even in the most artificial settings, time, or something like it, becomes necessary for coherence. Whether it's the frame rate of a rendering engine, or the step size in a physics model, there must be a way to move from one state to the next. And that movement gives rise to something very close to time. Not the time of clocks and galaxies, but the time of loops and cycles, of beginnings and ends, of cause and effect. There's also a strange parallel here with our own experience. We assume that time flows because we remember the past and not the future. We assume that there's a direction to events because entropy increases, but that direction, that forwardness, may not be a fundamental law. It might be a result of structure, of how our brains process events, of how the universe cooled and expanded. In a simulation, the arrow of time is not natural. It's designed. It's embedded into the rules. But once it's in place, it feels just as irreversible. Processes unfold. Agents learn. Change accumulates. And the only way to reset it is to rewind, to reload a previous state. In that way, simulated time can be paused, edited, erased. But it still feels like time to whatever is living inside it. If that sounds theoretical, it's because in many ways it still is. But the more we build simulations of weather, of traffic, of biology, the more we confront the fact that time, as experienced by a system, is inseparable from that system's structure, and that experience is not limited to humans. Machines keep time, software tracks durations, processes wait, resume, repeat. Not because they are aware, but because time in any form is what allows things to happen in order. Without time, even synthetic time, there is no change, no computation, no motion. And if computation is capable of generating complexity, of giving rise to awareness, then perhaps time, even simulated time can be inhabited. This leads to philosophical questions with scientific edges. What's the difference between time as we know it and virtual time? Is one more real, or are they simply built on different substrates? Does the substrate matter? If a simulated world contains agents with memory, expectation and awareness, and if they track time using consistent signals, then their experience of time is real to them. Even if the world can be paused, even if the clock has no gears, even if the tick is a line of code. In that way, simulated time becomes not an illusion, but a different kind of reality, one where the clock is hidden, one where the rules are written, not discovered, but one where time, in every meaningful sense, still passes, still structures events, still defines the difference between what was and what is, and for those inside, that difference is enough. Clocks are tools of precision. We build them to keep order, to track the flow of events, to measure duration. But for all their engineering, all their moving parts or atomic vibrations, every clock has a starting point, a zero, a moment that marks the beginning of its count. That starting point is rarely questioned. It's practical, arbitrary, agreed upon so that systems work, so that moments can be compared. But if you ask whether the universe has a clock, a master timekeeper ticking away the seconds since the beginning, you inevitably reach a harder question. If such a clock exists, who started it? Not who in a mythological sense with robes and intentions, not a figure, not a hand pressing the button, but what mechanism, what boundary condition, what initial state could have initiated time itself? Because a clock, at its core, is a sequence of events. Something happens, then something else, a change followed by another. If time is the result of change, then whatever brought the universe into being had to include, or create, the capacity for change. But if there was nothing before, no space, no time, no fields, then what does it mean to start? The Big Bang is often described as the beginning of time, but that's a simplification. The equations of general relativity allow us to extrapolate backward, compressing the universe into a state of extreme density and temperature. But they don't describe what happens at the singularity itself. That point where curvature becomes infinite and known physics breaks down marks the edge of the model. Beyond that, we don't have equations, we have speculation. Some cosmologists argue that time began at the Big Bang, that before it, if before even applies, there was no time. The clock in this view starts not because someone wound it, but because time is a property of the universe. No universe, no time. No need for a cause. Others propose models in which the universe is eternal, that what we call the beginning is simply a transition, a bounce from a previous state, a fluctuation in a quantum field, a shift in geometry. In those cases, the clock never needed to be set. It always was. But then we face a different issue. If time has no beginning, how do we reconcile that with the experience of causality? With the sense that everything follows from something else? An infinite past creates as many philosophical problems as a finite one. It leads to paradoxes of explanation. If time has no start, how can any moment be reached? How do you arrive at now from an infinite distance? We run into limits, not just of imagination, but of models. The equations don't break because of belief. They break because they reach conditions they weren't built to handle. Quantum cosmology tries to fill the gap. It replaces singularities with quantum states, spreads probabilities over paths, describes the early universe not as a sharp explosion, but as a smooth transition out of something else, a kind of no-boundary condition, where space and time both fade into a timeless quantum state. In that picture, the universe begins the way a wave begins, not from a point but from a rising curve, a shift in amplitude. The clock doesn't start ticking at zero. It emerges as the waveform stabilizes, as structure begins. But even this doesn't tell us who or what defined the rules. Because for time to unfold, there must be rules. Not necessarily laws written in stone, but conditions, relationships, structures that allow events to follow one another. Why those rules? Why this unfolding? Why any unfolding at all? Maybe the universe doesn't need a starter. Maybe the conditions for time are simply part of its existence. Maybe being includes duration. Or maybe our entire framework is too narrow. Maybe time is not something that starts or stops, but something that appears, locally, conditionally, at certain scales, like temperature or solidity. It depends on configuration. That would mean the question of who set the clock is misframed. The universe is not a device that someone turned on. It's a system in which time emerges, much as gravity or electromagnetism do, from deeper symmetries and broken states. But then we still have to ask what caused that configuration. What broke the symmetry? What allowed something to be rather than nothing? Some physicists argue that quantum fluctuations in a vacuum can give rise to space-time, that the nothing we imagine is not truly nothing, but a seething field of temporary states from which a universe can emerge. In such models, the laws of physics are baked into the fabric. The vacuum is structured. Rules are not chosen, they are consequences. Still, even there, we meet silence. Because if those rules exist, they must exist somewhere, in some framework, and if time is needed to apply them, we're back to asking how time exists without being created. Perhaps we're circling the problem the wrong way. A better question might be, what does it mean to say a clock exists? Clocks are observers. They mark relationships. If nothing changes, a clock is meaningless. So the existence of time, or a universal clock, may not be a matter of what set it, but of what experiences it. The universe may not need a timekeeper. It may only need events, moments, things happening in sequence whether or not they're being counted. If particles interact, if states evolve, then time is happening. The clock doesn't need to be external. It can be embedded in the unfolding. And from that perspective, asking who set the clock becomes asking, when did events begin? What was the first cause? What kicked off the first interaction? Again, we find ourselves at the Big Bang, or whatever came before it. Not because we can't imagine more, but because that's as far as our instruments and equations allow us to reach. Still, the question persists. Why did it happen at all? And that's where physics often stops and philosophy begins. Because physics is about patterns. What follows from what? It can model how time behaves, how it curves, how it's perceived, how it's altered by mass and motion. But it can't say why time exists at all, or why events occur in the first place, or why the universe is ordered rather than chaotic. Some thinkers suggest that time is a necessary condition for any observer, that any system capable of memory, awareness, or experience must exist in time, must measure change, however imperfectly. In that view, time is inseparable from existence. If something exists, time flows. And if time flows, clocks are implied, not built, not wound, just inherent. The clock is not a mechanism. It's a framework, a label we apply to change. And that change doesn't need a cause. It only needs to be. Still, the temptation remains to imagine a moment when the gears began to turn, when the system was activated, when the arrow of time first pointed forward. It's an image rooted in experience. Everything we know has a beginning, so we assume time does too. But perhaps time is the one thing that doesn't. Perhaps it's always been there, in some form, waiting to be experienced. Or perhaps it began not with a bang, but with a fluctuation, not with intent, but with probability, a random alignment, a tipping point. And from that moment, whenever or whatever it was, the seconds began. The universe expanded, clocks appeared, matter cooled, stars formed, and eventually someone began asking what time it was. Time is something we count, something we measure, something we feel. We build our lives around it, track it with calendars and clocks, record its passing in memories and history. But for all its familiarity, we rarely question its presence. It just is, like the air or the sky. Obvious, assumed. But maybe it's not. Maybe time isn't something the universe carries around like a built-in feature. Maybe it's not a flow, or a dimension, or a ticking that moves the cosmos from moment to moment. Maybe it's a story we tell to make sense of change, a structure we impose on what would otherwise be unstructured. Maybe there's no clock at all. If you remove the need for measurement, if no one is watching, no system is tracking, no motion is unfolding in comparison to another, does time still exist? Or is it something that only emerges once comparison is possible? In classical physics, time is absolute. Newton treated it as a constant background, flowing at the same rate for everyone, everywhere, regardless of motion. But that view collapsed over the past century. Relativity showed that time is tied to motion and gravity, that it bends, slows, speeds up, stops even, at the edges of certain equations. In quantum physics, time becomes something even more elusive, not necessarily included in the same way, sometimes not included at all. In some formulations, especially when describing the entire universe, time is absent from the most fundamental equations. You can describe the quantum state of a system without referencing a timeline. You only need relationships, correlations between configurations, one pattern compared to another. From that view, time is not a parameter. It's an emergent property. It appears when systems interact, when observations are made, when change becomes interpretable. But what if the entire idea of a clock, the notion that there is something steadily ticking beneath the surface of the universe, is just an artifact of perception? What if time isn't something the universe has, but something the mind creates? This isn't just a poetic idea. There are serious physical models built on this kind of reasoning. In these models, the universe doesn't evolve in time. It just is. A block, a complete configuration of all events, all moments, all structures, with no need for time to make it real. The block universe view, as it's sometimes called, suggests that the past, present and future all coexist. There's no flow, no becoming, just a four-dimensional structure, with time as one of the coordinates. But we don't experience it that way. We experience now, we remember before, we anticipate later. So where does that experience come from? Maybe the feeling of time is a cognitive process, a way the brain tracks sequences, links memories, forms continuity. The present moment, what feels like the moving edge of time, might be a construction, an illusion created by how information is processed and stored. And if all of this is true, if time as we know it is experiential rather than fundamental, then there's no universal clock ticking away beneath reality. There's only change, and the structures that interpret it. In physics, this leads to proposals that time is not primary but secondary, that it arises from entanglement, or from thermodynamic processes, or from coarse graining, the statistical smoothing of underlying detail. In some theories, time emerges only when a system becomes large and complex enough. Below a certain scale, there is only state, no direction, no ticking, no history, just configurations. And yet, even in those configurations, something happens. Probabilities change, wave functions evolve, fields fluctuate. It might not be time in the way we recognize it, but it's structure, progression, something like order. Still, if there's no fundamental clock, then there's no reason to assume the universe is moving forward, or even moving at all. Maybe we only see motion because we exist within it, like fish in a current, unaware that the river isn't flowing past them. They are part of it. We search for time in everything. We interpret cosmic expansion as a history, as a story with a beginning and an end. We map events onto timelines, date fossils, calibrate clocks. But the universe might not keep track. It might not count seconds or care about age. It might just exist, fully formed, with every moment already part of the structure. If you took that view seriously, then questions like, when did it start? or how much time has passed, become less meaningful. There was no ticking clock at the beginning. There is no master timekeeper measuring the seconds as galaxies form or fade. Instead, there are only relations, states connected to other states, not cause and effect, but correlation, not evolution, but geometry. This doesn't make experience less real. It doesn't deny the fact that we feel time passing, that we age, that the world seems to change around us. It just means that those feelings might be tied to our perspective, not to the underlying structure. The clock may be in the mind, not in the cosmos. Of course, most of the time, this distinction doesn't matter. We use time as a practical tool. We build calendars, track pulses, measure intervals. We synchronize systems, coordinate activity, structure memory. Time works, but working and existing are not the same. Friction works, but it's not a force. Heat works, but it's not a substance. Maybe time is the same, a phenomenon, not a thing. A way we describe what systems do when they change. And change doesn't need a clock. It only needs difference. So maybe, at the most basic level, the universe is just a landscape of differences, patterns, states, and time, as we experience it, is a way of moving through that landscape, not physically, but mentally, by linking memories, projecting futures, forming continuity. If so, then time isn't out there. It's in here, not a dimension, but a description, not a tick, but a tendency, a way of saying that this is not that before was not now. In that framework, there's no cosmic clock, no master rhythm, only systems behaving in patterns that, at the right scale, look like history. That perspective doesn't make time less important. If anything, it makes it more mysterious. Because if time is something we construct, even partially, then understanding it means understanding ourselves, our cognition, our memory, our perception of change, and our inability to experience reality all at once. So maybe there's no clock at all. Maybe the ticking is something we bring with us, a metronome of the mind marking intervals in a world that doesn't know what intervals are, a rhythm applied to a cosmos that, at its heart, might be silent, still, uncounted. But within that stillness we find movement. Within that silence we hear sequence, because we are not outside the universe watching it tick. We are inside it, measuring the difference between what is and what was, and calling that difference time. If you've made it this far, then you're still here, wherever you are, and just as importantly, whenever you are. Maybe you're listening at the end of a long day, wrapped in the quiet stillness of night, the hum of distant traffic fading outside your window. Or maybe the sun is just beginning to rise where you are, casting that first gentle light across the wall, a moment that belongs only to you and only to now. And yet, what is now, really? After all this, after exploring stars and clocks and light and entropy, singularities and simulated worlds, the question lingers, not because it's unanswered, but because it may not need an answer at all. Maybe now is just whatever you're experiencing, not a universal point, not a location on a master timeline, just a state, a configuration, a shape your consciousness moves through. Maybe now is where you are, whenever you are. The idea that the universe has a clock is comforting in some ways. It offers a sense of order, a rhythm to follow, a sense that things are unfolding with purpose. But the more we look, the more we find that time doesn't cooperate with that picture. It bends, it breaks, it vanishes at the extremes, and yet we go on living inside it. We wake up, we sleep, we remember, we hope, we miss things, we wait. These are all acts of time, not because they appear on a clock, but because they require a sense of before and after, because they anchor us, but those anchors are personal. Your memories are not on anyone else's timeline. Your experiences are not marked by cosmic coordinates. The things that matter to you, that you carry from one moment to the next, don't follow a gravitational curve or a Planck scale rulebook. They just happen. They accumulate. They build a kind of internal chronology that's yours alone. Maybe that's what time is when you peel everything else away. Not an equation or a dimension, but a quiet thread tying your experiences together. You don't need to know when the universe began to feel the weight of a day. You don't need to calculate entropy to miss someone who's not there anymore. You don't need to understand relativity to wonder how much time you have left. You just need to be alive and paying attention. There's something humble in that. A reminder that science doesn't have to shrink the world to explain it. It can expand it, open it, make room for experience. Because in the end, all of this, the theories, the models, the metaphors, they're ways of describing something that you're already part of. Not outside, observing the universe as it ticks, but inside, embedded in the change, wherever you are and however you are. Even the act of listening is temporal. You didn't hear these words all at once. They arrived in sequence, one after another. You processed them, maybe remembered some, maybe let others drift by. That drift, that unfolding, is your time, and it's different from mine, from anyone else's, not because the laws are different, but because the experience is, and maybe that's all time ever needed to be. Not a thing to measure, not a mystery to solve, just a way of living, of noticing, of moving through a world that doesn't stop changing, even when you do. So wherever you are in this moment, whatever your day has been, whatever your night still holds, know that this now, this exact point of awareness, is as real as anything in the cosmos. It may not be on a universal clock. It may not be repeatable or measurable or provable, but it's yours, and that's enough. If you found this journey calming, or thought-provoking, or even just a little easier to drift off to, you're welcome to return any time. Time doesn't have to be measured. It can be felt, revisited, remembered, and until next time, however far or near that is for you, rest well. Time will take care of the rest. Thank you for spending your time here. If this brought you a sense of quiet or sparked a question you hadn't thought to ask, feel free to stay connected. You can subscribe or simply come back whenever the night feels long or the mind won't settle. New thoughts arrive here often, softly. Until then, sleep gently.